All right. Good morning. Good morning, everyone, and happy International Day of the Woman. We are here for a very exciting session on the last day of March meeting. I do not have it in front of me, but it is Industry, Innovation, and National Security, Finding the Right Balance. I'm very excited for our panel of speakers, and I'm hoping they'll tell me about how my title might be all wrong. All right, so first up is Dr. Weber, and she will be talking about the quantum computing industry and national security. What tools will work? Thank you.
Thank you, Lauren. And let's see, is my mic on? Yeah, okay, it's hard to tell. My name is Kate Weber. I work on Google's quantum computing team, Google Quantum AI, as the head of governance. So I handle government affairs and other kinds of outreach for the team. And I'm going to talk today about the quantum computing industry as a case study for an industry that is working on a technology that is very relevant for national security, getting a lot of attention for that relevance. But a lot of the innovation is happening in the private sector. And what does that mean for how we control information? What role does the private sector play? What policies exist and maybe don't exist for this, this industry that we're in? So I assume that most people at APS are, somewhat familiar with quantum computing, but just to level set, often I'm talking to policy people. So, this is the what is quantum computing slide. Quantum bits or qubits are a fundamentally different way of storing information than it is stored on a classical computer, which stores bits, zeros and ones. You can have one of these two states on a classical computer. On a quantum computer, the qubit can be in a 0 or 1 state, and it also can be in both at the same time. This opens up lots of different problem spaces and allows you to tackle different kinds of problems. And so that is why we are working on quantum computers. And this is important in thinking about the national security implications of the technology, because those implications come from the potential applications of the technology, right? So there are quantum computers will be, I would say are not yet, but will be a powerful tool for computation. They will allow us to solve problems that we cannot solve with classical computers. There are a few examples of kinds of algorithms that we, or problems that we expect to have speed-ups on quantum computers and the sort of general application areas for those. So on Grover's algorithm, unstructured search, the important one for today that I'll talk a bit more about, factorization, right? Being able to solve Shor's algorithm. This is the I would say, main drive behind the US and other national security communities' interest in quantum computing, because large-scale quantum computers are expected to be able to break much of today's public key encryption, which is a very relevant national security risk. We'll talk about what national security means and why that's the case in a bit. Speed-ups for solving differential equations. Some of the earlier applications we're expecting are in the quantum simulation space, so simulation of materials and quantum machine learning. And I'm not going to go into detail, but the other point I wanted to make on this slide, in addition to pointing out the factorization application, is that we expect a very large problem space that quantum computers will be able to tackle that we can't tackle today. We expect a lot of benefit from this technology, so it's not like we're just building it so that we can factor large numbers. Like there is, and this is relevant, I think, in a broader sense for national security too. There's potentially a lot of economic benefit, a lot of societal benefit from this technology. So it's not like, oh, we should just shut it down because it's going to be bad for national security. We need to kind of keep, to the title of this session, we need to keep that balance in mind. So now, what is national security? And let's talk a bit more about why quantum computing is relevant and of interest for national security. So this is the Department of Justice definition of national security. And the DOJ website also says that this is the most important mission of the US federal government, protecting national security, right? So that's why we see so much attention on it. Encompasses the national defense, foreign intelligence and counterintelligence, international and internal security, and foreign relations. And then there are some examples of activities, some of which, for example, export controls, we'll talk a bit more about in this talk, that the government undertakes to protect national security. I think that if you think about the Shor's algorithm and breaking encryption example, this foreign intelligence and counterintelligence is probably the most relevant for that specific application, right? If a foreign government develops a quantum computer before the US, and then especially if they then don't tell us, they could start breaking encryption of lots of sensitive intelligence information. That would be very bad. This is probably a whole nother talk, but there is a solution to that problem. There are post-quantum cryptography algorithms that have been developed by NIST. That standardization process is close to finalization, and then we have the task of implementing those across all of our machines. But there are a couple more points I wanted to make on this, what is national security slide. I think that the definition of national security has also been expanding a bit recently to think about what is in kind of the economic benefit side of things, right? It's also important for our national security that we have a thriving economy. And so we can't shut down technology development because that will put us behind on the economy side. And ultimately, we'll lose out on national security because we'll lose this race with adversaries to develop these technologies. I should say, in addition to this encryption example, there are other potential applications for quantum computers in national security relevant areas, right? If you can simulate materials better, you can imagine there might be applications for that in weapons development, right? Obviously important to think about those and to think about how to control the development of those. So the importance of, the relevance of quantum computing for national security and just also for kind of national economies and society, I think you can get a signal of this from the national strategies and investments that we've seen in recent years in quantum computing. So I'm not going to go through this list, right? It's a snapshot of the many countries that have announced national strategies and investments in quantum in recent years, and also there are many, and this list could probably be longer now, bilateral, multilateral agreements either focused on quantum between the US and other countries, or they're a sub-focus of a broader agreement like the Australia, UK, US partnership, the US-EU Trade and Technology Council, et cetera. I've sort of been hinting at this as well, but of course there's also a very large investment from the Chinese government in this technology, which is why the US government is part of the reason is particularly focused on it. There's a lot of focus, as you probably have all seen, in Washington on the US-China competition dynamic these days. But it's very hard to figure out exactly what China is investing, but it's a lot, yeah. But there's also, I also want to point out, so many countries have announced these investments, but actually the innovation in quantum computing is happening in the US and US allied countries. I think most would say it's happening largely in industry, right? The Chinese government is funding most of the development in China, but in the US, the government has done a lot of work on quantum technologies, but the most advanced quantum computers largely sit with private industry. And this, not sure if this slide is maybe a little bit hard to read, so I'll kind of go through it, but this $1.76 billion is a global startup investment number for quantum technologies broadly. So there are other kinds of quantum technologies, not just quantum computing, but wanted to just give you a sense of scale. And then the US government investment in quantum technologies in that same year, 2022, was $918 million. So still very large, but not as much as the startup investment. And then that's not even counting the investment from large companies. And there aren't really published numbers on the investment here, but Google, Amazon, Microsoft, IBM all have quantum computing teams. This is a different dynamic than many past national security relevant technologies, right? Nuclear technologies, semiconductors. A lot of the early innovation work for those technologies was done in the US government, which meant there was a lot of control over how that innovation was done. And so this presents kind of a policy challenge. There's this very national security relevant technology that is mostly a lot of it anyway, is being developed in the private sector. I also just want to talk a little bit about the timeline for this technology, because I think it's easy to kind of hear all of this and get very worked up and say, we've got to do something like now, this is an existential crisis. We are quite early on this road to a useful quantum computer. I've put Google's roadmap here as just to give you a sense. Obviously, other companies have their own roadmaps, but I think most people would say that we are at least a decade away from a computer that is capable of breaking encryption. Google's roadmap has 6 major technical milestones to build what we call an error-corrected a fault-tolerant error-corrected quantum computer. And we've achieved the first 2 of those, which means the first milestone was showing that we could do a calculation on a quantum computer that would have been impossible, impractical, taken thousands of years to do on a classical supercomputer, a proof of principle. This is not a useful calculation, right? So and in fact, today's quantum computers have not yet shown to be able to do anything with real world usefulness, let alone breaking encryption. Our second milestone we announced last year. This was to show that as we scale up the number of qubits we're using for a calculation, we can use something called quantum error correction to reduce the error rate for the system. And that's a big deal because these are very error-prone systems, and this is one of the biggest challenges in building a large-scale quantum computer is to correct those errors. We also need to do a lot of other things. And then you see there are 4 more milestones. We're targeting our next milestone in 2025 plus. So, and yeah, this milestone 6, we don't expect that to happen before the early 2030s. And that is milestone 6, you'll see we estimate that to require about 1 million physical qubits. We have about 100 now. We expect to need something on the order of 10,000 physical qubits to break Shor's algorithm, so we're even further away from that point. And then this is just this is our business milestone roadmap, which gets a little bit more at this point of like, hey, today's quantum computers don't do anything useful. The next milestone we're looking toward is some kind of real world application for these early stage, what we call NISC, noisy intermediate scale quantum processors. And this is just a little bit more about this next milestone that we're working towards, and that's to dramatically reduce. So we achieved this milestone where we could show that error correction works. As we increase the number of qubits, we reduce the error. The next milestone, we have to bring that down a lot to build what we call a long-lived logical qubit that can do 1 million calculation steps before giving an error. So that's not to say that these processors aren't at all useful, but they're mainly being used for scientific discoveries these days. And I'm not going to spend a lot of time on this slide, but again, just want to kind of level set on where we are and how worried we should be and how we need to think about implementation of policies and procedures to protect sensitive information, what that timeline looks like. Again, I think I've kind of already, so this next challenge, demonstrating some kind of commercial relevance for a quantum computer and an application that's not possible on a classical computer is the next challenge. So this is kind of a sampling of experiments that have been done so far. Some of them are useful. They're kind of to the right on the utility axis, but easy to do on a classical computer. This is the hardness axis. And then some are hard. This random circuit sampling is the algorithm that we use to show a quantum computer could do something a classical computer couldn't, but it's not useful. So the other thing I'm going to transition now and talk a little bit about these. What are the potential policy mechanisms? How well might they work? What are the gaps? And I want to just mention briefly, people are building quantum computers using different qubit architectures. We are using superconducting qubits. Others are as well. But there are many approaches to building qubits. And this is important because one of the main mechanisms that exists for controlling this technology is export controls. But in order to design an export control, you need to have a threshold or some kind of, they call it choke point technology that you control. And the idea is that this is a technology like the US has and our adversaries don't have. And so if we don't export it, then they can't use it to develop their industry. When you have many different qubit architectures, the support technologies that you need to build these quantum computers are very different across these different kinds of qubit architectures. And that means that it's not easy to design something to control that is going to work for all of these. And we don't know which of these is going to be the one that is successful first in building this large-scale quantum computer. It's another sign of this early stage of the industry. And it's particularly, like, the existing policy mechanisms just don't work very well to control an industry that's at this stage, I think. So what are these existing policy mechanisms? So export controls. So the basic idea, you have some kind of choke point technology. Say there's for our superconducting quantum computers, the chips need to be very, very cold. We use dilution refrigerators to cool them down. This is in the early days, one of the technologies that you'd hear the government talking about controlling, right? Because there are a limited number of companies that make them. If you control who can get the dilution refrigerators, that limits who can develop superconducting quantum computers. That, again, I think has since been acknowledged to not be a great option because that only helps you with one of these qubit architectures. Then you're advantaging certain companies. You're potentially and a broader issue with export controls is you're potentially disadvantaging the US with respect to competition because US companies have to comply and others don't. There are foreign investment controls. There's CFIUS is the mechanism for controlling US investments in foreign companies and foreign investments in US companies. And there's a process for notifying and getting approval for those investments. There are potential supply chain regulations, and there are sanctions. So these are, in thinking about these policies and whether they'll work, I think it's important to ask some questions. So we talked a bit about export controls. Does the export control, when you're thinking of how, you could also control a quantum computer based on number of qubits is something that's been proposed. But that doesn't work very well because you can have different quality qubits. The number of qubits doesn't necessarily tell you how powerful a quantum computer is. And what is the specific risk, the specific application or risk that you're trying to address? Are the controls architecture neutral, right? Would they apply across all of the quantum computers that are being developed? And then this last point, to this point of are you disadvantaging US companies? Are they multilateral? Are other companies where other countries where quantum computing companies sit also putting in place similar export controls so that US companies don't have the extra burden of an investment required to comply with these controls when maybe competitors in other countries don't? And so, of course, we're not expecting adversaries to put in place export controls, but at least for US allies, and there has been a big effort from the government to work with allies to put in place their own export controls. There is a multilateral agreement, the Wassenaar Agreement, to do this across multiple countries at once. That is broken these days because Russia is a member of it and is never going to. It's a consensus-based body. So everybody is kind of acknowledging that we can't really use that the way we would have previously to get everybody to put in place the same export controls at once. Another note just on export controls, the quantum computing US industry is not actually really exporting anything these days. The way export controls work is to export to certain countries. Based on these thresholds, you need a license. And we're not actually doing that. But there's also something called deemed exports, and that means that we also need licenses for nationals of those countries working on our teams. And that is really the main impact on an industry like the quantum computing industry of export controls. And it's a big impact because quantum computing, like all emerging technology, one of our biggest challenges is attracting talent. So, it is important that this be done thoughtfully. So federal supply chain regulations. So let's talk about what does that mean? That means like if the government is procuring something, they can put in place rules for what companies need to comply with in order for the government to buy that thing. So the sort of questions asked here, how much is the government actually procuring? And is it likely to be a major customer in the future? So I think the answer to that latter question is like probably yes, the US government will become a major customer for the quantum computing industry. But again, to the point that it's hard to regulate at this stage, it's not right now. I mean, it's maybe the biggest customer that's out there because there aren't very many in general, but it's not really a way to, I would say, fully address this problem. Investment controls, if you're gonna control foreign investment, like how common is foreign investment in the industry? How critical are foreign investments to the US supply chain? In the case of the quantum computing industry, I think the answer is from adversarial countries that would be controlled under CFIUS, the answer is not very common. We do have a lot of suppliers, like in Europe, for example. But, and then sanctions. Like sanctions are a very specific policy mechanism targeting people and entities in a few countries, and I also don't think that this is particularly relevant for our industry. So there's also like companies can and do things on their own for their own commercial interests to protect their security, that are aligned with protecting national security. And so I think one question to ask is how can the companies and governments work together better to align what we are doing with national security interests and to kind of understand maybe if there's information that the government has that we don't have that we should be applying to our internal processes. We also don't want our IP to leak to competitors, so we have an incentive for protecting our information as well. But of course, we also need to collaborate, so there's a balance here. But what do? I mean, we have physical security programs, right? Like protecting the actual hardware, controlling who has access to it. Cybersecurity, this is, I will say, like companies, Google has pretty sophisticated cybersecurity teams and mechanisms. Because of our scale and our business model in general, we can benefit from those. Some of these problems are harder for startups. And then insider risk, which gets to this like export control point. Export controls, you need licenses for nationals from certain countries to work on the technology, but of course the risk that you're trying to address there is that they will be working with a foreign government and leaking that information, or the risk the US government is trying to address. There's a much broader risk though of company employees sharing information, whether intentionally or not, externally. And of course, in order to share information with a foreign government, you don't need to be a national of that government. So the industry is in early stage. We have many big challenges ahead. There's like going back to the title of the session, when we think about this, how to balance national security with innovation, I think it's really important to think about the stage of the industry, these big challenges. We have to go from a scale of about 100 qubits to a scale of about 1 million before we have a mature quantum computer. We need to improve the qubit quality a lot to do that. We have to scale to larger chips. We have to scale all of the components around the quantum computer in order to do that. We have to develop our supply chain. It's the supply chain today, we're developing a lot of components in-house because it's very immature. We have to develop more applications, right? We have a lot of areas where we expect applications, but we need to do more work to develop specific algorithms that we think will be commercially relevant. In fact, Google is funding an X Prize on this topic that we announced earlier this week to incentivize more applications. And we need to continue to develop this workforce, both through domestic education and through immigration, which is why the export control piece is impactful and relevant. And so then I think that there's so just to kind of talk about what we think should happen, we do believe that targeted export controls are probably a good thing in some cases. It's just not clear how that would be implemented for the quantum computing industry at this point, but we've had a lot of discussions with the government and others in industry to try to align on some kind of approach that might work there. But that's not going to be the whole solution, and if done in a non-targeted way, could actually be really damaging for the speed of innovation, which in the end is not going to help US national security. So one question here is, are there mechanisms, like could you set up some mechanisms to have better communication between the government and the private sector on what we should be doing to mitigate risks? What specific risks are there? Like, could we set up some mechanisms to share classified information with certain private sector employees so that we could implement this more effectively? Because we do have conversations with government entities now, but frankly, we don't learn very much from them that can help us. Are there incentive-based approaches? So some of the ideas that we've heard that I think are really interesting are like, could you set up a situation where there's some kind of challenge and the first team to build a quantum computer that can do X or that meets X, achieves X parameters, gets some money, some like significant amount of money. But in order to get that money, you have to adhere to certain security practices that the government defines. These kinds of things might work better to get the private sector to put in place these new kinds of mechanisms. And then like the last sort of just question to ask and to really think about is, how should policies to control risk be balanced with those that invest in US leadership? And this is, I haven't really talked a lot about this in the talk, but this is, I think, probably the biggest one. And it's not a very good time for as everybody in this room knows, for like the R&D budget in this country. And there's a US National Quantum Initiative that was supposed to be renewed last year, and it hasn't been renewed yet because of the dysfunction in Congress. And I think this is really the biggest problem. Like, you can do all you want on the export control side, but if we're not investing in US leadership, it kind of doesn't matter. And it could end up being like, okay, let's clamp down on the private sector, which is where the investment is actually still happening, and then we're just kind of shooting ourselves in the foot twice. So that's, I mean, I wanted to, that's the conclusion. There are some targeted things we can probably do, and I think most in the industry are very interested in engaging on this and figuring out what those things are that are going to be effective, that will allow us to continue our current speed of innovation, but also like protect national security and protect our own commercial interests at the same time. But it's the policy mechanisms that exist are not very well suited to do that, and there's this broader political issue around investment that is a problem. Yeah.
Thank you. We will now take questions for our speaker, and if you do have questions, remember to come down to the mic so that the audience out there and the recording can hear you.
Terrific talk, thank you. You mentioned a 10-year timescale for some of the big payoffs. Are there milestones along the way that might bring some financial return to the companies that are investing so heavily, so that we'll make it through this sort of frothy bubble we're in now? I mean, it's stunning to walk out onto the floor and see so many quantum, investing in quantum. Is there a way to maintain the investment long enough to get to the promised land?
Yeah, that's a great question. And this is my first March meeting, but I have heard that this has been a big transformation and like the exhibition floor and the talks at this meeting over the past 5, 10 years. We do expect to have kind of targeted applications in the next few years. I think the jury's still out on how much revenue those might bring in, because we kind of have ideas for what the algorithms are and the kind of application areas, but until you're able to actually run them and like test them out for those applications, it's hard to know how useful. And this is actually part of the reason that we announced this prize earlier in the week as well, because that like making that connection from the algorithm that can run faster to what the application is I think something that's quite difficult and maybe could be happening more in the community. It's hard to say if that's going to bring in enough revenue to fund the continued innovation. It's like telling that a lot of the investment is from large tech companies that can make these investments without having to necessarily bring in the revenue immediately. But there is also a lot of push for the government to step in there and invest in companies and testing out early stage applications to help bridge the gap. Yeah.
Okay.
Thank you for the talk. So you've talked a bit about foreign actors in foreign policy. Do you have specific recommendations, for example, for who to work with and how to interact with other countries, let's say via NATO, or you've mentioned Europe? What is your recommendation for collaborations and partnerships? Or do you think the US should actually go it alone?
The US should definitely not go it alone. And this is a great question. I think this has actually been a big focus of the US government in the last couple of years as well. That's why we have this proliferation of the bilateral agreements, I think. So it has been a little bit hard to like say, okay, here's what those government to government interactions should lead to. The biggest thing that we're focused, well, 2 big things, maybe 3 big things. The supply chain piece, the industry is a global supply chain, and I think that this like figuring out how to invest in strategic parts of that supply chain globally so that the industry can progress faster and companies are not having to invest themselves in developing all these components for the quantum computers. That's a really important point, and it's something that ideally would be done collaboratively between governments. There's the workforce piece, like it's a global workforce. What can we do on working with others are there exchange programs? Are there things we can learn from what others are doing and kind of implement programs that other countries have successfully implemented and vice versa? On the workforce side, is there more we can do? We've had a lot of collaborations with companies, research groups internationally, particularly on the kind of algorithms application side. But most countries are, I think, viewing this technology. They want to collaborate, but they also have very nationalistic approaches to how they're developing the technology, and that comes out with different terminology in different countries. The US government will talk a lot about national security. Europe talks a lot about digital sovereignty. It's kind of essentially the same thing. And so that can be a barrier to these kinds of collaborations on applications, even on hardware. And if there are things we can do to like encourage that collaboration rather than discourage, as it sometimes has been in the past, that would be great. Yeah.
Hello, can you speak some more about the impact of deemed export controls on Google's work in quantum computing? You referenced that, but have you seen significant shifts in the way that those controls are applied in recent years? And if so, can you give some examples of how the effects that it's having and any changes you think should be made?
I mean, in nationals of countries that are named in an export control. So there are existing export controls for superconducting electronics, which we at Google are implementing, and superconducting quantum companies are implementing. And the time that you need to wait for a license, for a deemed export license, has increased pretty dramatically in recent years. So you'll have people, you hire people and then can wait sometimes years before they're able to work on what they were hired to work on. Sometimes they're given a license, but it's like very narrow and they're not able to work on what they were hired to work on. And we've had some cases where that's like the case, or somebody's waiting for a license and they like get a green card before they can get this, and then then they can work. But like the green card process is notoriously, it's not a fast process, right? And it's sometimes faster than this deemed export process. I've heard some interesting ideas, and I'll wrap up, around like, I've heard people at the State Department, for example, float this idea that you could like somehow pre-vet people who would like to work in this industry and are nationals from countries of concern, so that like a company could hire them and not have to wait 2 years for them to work. And that might make it would make it easier for companies. It might also make it easier for people to get these jobs if they're from these countries of concern. So, yeah.
Let's thank our speaker again. All right, and now we have Dr. Liddle from NIST, and he will be talking about the trade-offs and tensions in R&D from facilities to programs.
All right, so good morning, everyone. Thank you, Lauren, for the invitation to speak here, and thank you all for turning out early on a Friday morning. I know this has probably been an exhausting but hopefully exciting week for everyone. So before I dive in, I want to give you a little background about myself, because that is what is informing my perspective on industry and innovation, and that's really going to be the focus of my talk. I'm not going to talk so much about national security, except to say that NIST, as the Department of Commerce, thinks a lot about national security in the context of economic security, and economic security depends on us being successful economically. And in the context of this talk, I'm going to focus primarily on the role of innovation in driving economic success. So my background is material science by training. I spent over a decade at Bell Labs working on developing an advanced lithographic technology. And for the past 3 decades, I've sort of been in and around the semiconductor industry. But after I left Bell Labs, I worked in a couple of nanoscience user facilities, both of which had strong internal research programs as well as the externally facing user component. So a lot of that experience is sort of informing what I'm going to be discussing in the next few slides. So when I looked at the title of this session, it said Finding the Right Balance, and I thought, well, you know, is there a single balance point? And back when I worked in the advanced lithography department at Bell Labs, one of the technologies we worked on was proximity X-ray lithography. And the way that you controlled resolution in that technique was to just adjust the distance between a mask and a substrate, and you had only 1 degree of freedom. And that made life very difficult. It was also not very interesting. So rather than trying to think about a single balance point, I wondered, well, you know, do things get more interesting and more exciting if I have more than 1 degree of freedom? So you can see this fellow here who is probably excited, experiencing multiple degrees of freedom. But thinking sort of more broadly about the possibilities and the various balance points, I think is interesting and exciting. And when you have more degrees of freedom, that allows you to be a lot more creative in the types of solutions that you can come up with. So what I hope to show you as we go through the rest of the talk, or what I hope to encourage you to do, is to think creatively about the various balance points that we might find in order to increase the pace of innovation. And in fact, when I was thinking about what to say in this session, one of the questions I think is always good at the beginning of any endeavor is really to ask the question, well, exactly what is it we're trying to do? For those of you familiar with DARPA and the Heilmeier Catechism, that's the first question. What is it you're trying to achieve? And as I said before, I think in order to bolster our national security, we need to increase our economic security. And what that means is that we need to improve our ability to innovate. So when we think of innovation, I'm going to use a particular definition here. When we think of innovation, typically we have sort of a narrative in mind that I don't think is accurate. There's sort of a discovery that happens, and then there's some development, and at some point the market sort of pulls that discovery into the commercial realm. Instead, we need to think of innovation a little differently, and I'll say I'm drawing here on ideas that are in a book actually published by a former Bell Labs colleague of mine and some of his collaborators, called Inside Real Innovation. And what they point out is that innovation is not a linear process. It's actually a highly iterative process. And those iterations happen between the domains of the technology, which I think most of us are interested and excited by, but it includes the critical pieces of implementation. How are you actually going to take your brilliant idea and ultimately get it manufactured, and the market. So how are you going to deliver something that people care about and are willing to pay for? Because unless you can do that, you haven't really innovated. And innovation is an embodied idea or breakthrough in the marketplace. And getting to an innovation requires frequent and ideally rapid cycles of iteration between the technology, the implementation, and the marketplace. And I have a little box on the side here in red. I was trying to think of a suitable metric when you think about cycles of learning and innovation, and I'll say these are not NIST-approved units, but a useful metric, I think, is sort of the amount of learning you get per dollar spent and per time invested. So if you think about innovating, you want to sort of maximize that metric because that means you're actually moving more rapidly down the pathway to actually delivering something that can have an economic impact. So, as I said, I've spent a lot of time in and around the semiconductor industry, and we're at a really interesting point here. So this graph is supposed to represent sort of three axes, if you like, of potential innovation. On the one coming out towards you, we have sort of the continued scaling, which people tend to think of as being embodied by Moore's law, though I would argue that's a much broader concept, in fact. Tremendously difficult and challenging technically, but something that major companies are making progress towards in conjunction with various R&D organizations. But on the sort of the horizontal axis, we have tremendous innovation in terms of the different kinds of functionalities that can be added to semiconductor systems. So those can include sort of analog and RF, all the way through to things like bioelectronics. So there's really a tremendous range of technologies now that rely on the semiconductor manufacturing platform that we're starting to integrate into really complex and highly performant systems. And I was watching a video the other day on the Apple Vision Pro. I would say here that NIST does not endorse commercial products. This is just a representative example. But if you look at that product, it embodies not only some spectacular processing power in the form of a very advanced chip, but there are displays and there are sensors that do all the tracking and allow you to maintain sort of the virtual overlay on the real world. So there's a tremendous amount of embodied technology in that is taking advantage of our ability to fabricate and integrate all these different sorts of things. And then on the vertical axis, we go all the way from sort of materials to the end application, and we need to make sure that all of that works seamlessly together in order to deliver these highly functional systems. So for those of you not familiar with sort of the process of creating semiconductor technology, it really does take an ecosystem to do that. So this is just a sort of a very high-level view of what it takes to deliver a functioning semiconductor device. So obviously you start with your system specifications, and then there's an architectural design process and a functional design and logic synthesis and then a technology mapping, and then you finally get to the physical design. And with modern chips where you may have tens of billions of transistors in a single chip, there's a huge amount of work associated with verification. And you get to an actual physical layout. And then there's this one box marked fabrication, and it really hurt me to put fabrication into one box because that's what I've spent a lot of my career worrying about. And that encompasses, the somewhere between $10 to $30 billion advanced fab and all the processes that go in that, and the in excess of 1,000 steps that are required to actually fabricate a chip. But I digress. And then finally, test and measurement and packaging of a finished semiconductor device. So this is all good. And each of these boxes represents a fairly large number of individual companies who satisfy these sort of various niches in the ecosystem that all have to play together to be able to deliver the semiconductor technology. So when we think about what needs to happen here in order to keep innovations flowing in the semiconductor industry, you'll hear the phrase innovation across the stack. And what that means is that we need constant communication all the way from materials through structures, devices, circuits, packages, and so on up through applications, because decisions made at any one of those levels will have ramifications and impacts for the steps above and the steps below. So it is possible to make a materials choice that has an impact on applications and vice versa. So we need this sort of constant communication between all levels of the stack, between all the players in the ecosystem. So with that as background, I want to sort of take a little bit of a look at the history of the semiconductor industry. So years ago, I joined Bell Labs back in 1990. It was a wonderful place to work, sort of one of the legendary industrial R&D labs, and there were others like IBM and HP and Xerox and so on. And the sort of the transactional costs of moving around that innovation cycle from technology to implementation to market were really very low because those companies were vertically integrated. So even if you were working on sort of fundamental R&D, and even though you may not have sort of gone out to communicate directly with the factory or to the people selling the services, it was sort of just in the air what the important problems were. So that rapid iteration between technology implementation and market was really something that occurred very naturally. But of course, those companies that I've listed and others were essentially monopolies. So it was very easy for that sort of vertical integration, for those cycles of communication to occur. But of course, we live in a highly competitive economic environment. people are not necessarily happy dealing with monopolies. So, one way or another, those corporate R&D labs came under tremendous pressure, as did the companies themselves. And the result was a disaggregation and a dramatic increase in operational efficiency. But instead of vertical integration, you had sort of horizontal integration, the development of silos now with materials companies, equipment companies, design software, and so on, all the way up to the system integrators. And what that has done is to make the transactional costs, if you like, of going around that innovation cycle much larger. And that's really one of the key points of this talk, is to encourage everyone to think about ways of lowering those transactional costs and allowing us to go through those cycles of innovation a lot faster and a lot more efficiently. So, again, what are we trying to do? Ideally, increase the pace of innovation. So I'm going to spend just a couple of slides talking about the technology piece. And again, I think most people here are probably most excited about the technology piece. I know I certainly am. And this is one of those sort of trade-offs and tensions pieces that the title of my talk suggested. We hear a lot these days about going from lab to fab. And I'm not sure that's actually a terribly useful concept, because when you think about it, there are thousands of R&D labs and only a handful of fabs. And in an R&D lab, you have a tremendous amount of flexibility. You can try new materials and processes and so on. But that flexibility has a downside. Anybody who's worked in a research facility knows that at some point the critical tool that you depend on will become an experimental platform for a graduate student who does not necessarily know what they're doing. They try something and that tool is offline for the next 6 months while you try and recover it. Whereas in industry, you are trying to achieve an extraordinary level of reproducibility because you're making product, and you don't have that flexibility. So there's this sort of natural tension between the two. And again, this sort of lab to fab idea doesn't make sense just from a numbers perspective. You have, again, thousands of R&D facilities and only a handful of industrial facilities, and they are not going to let you come and try out your great new idea. So one of the things that we've been working on at NIST is to try and figure out how we can bring the fab to the lab and sort of improve the ability of people working in R&D to deliver technology that is actually industry relevant. So again, the goal here is to reduce the incremental cost of innovation. And the challenge is that, if you want to make a chip, it's an expensive proposition. There is, you have to do the design. Ultimately, maybe you need software licenses to do that design. You might need to pay for circuit IP. I'll talk about IP a little bit more later. And then you finally get to the point of making the chip, and that's all expensive. But once you've done that, you can continue to produce those chips. And ideally, if those chips are generally useful, you can help reduce the incremental cost of innovation. And the idea here is to build platform devices that embody a lot of intelligence in the underlying circuitry, but allow people to build experiments on top of those. So a simple example would be, I'm interested in exploring a new non-volatile memory material. I can get one of these chips. It's got a lot of embodied measurement technology in the underlying circuitry, but it's configured in such a way that I can build my devices on top of that and do a large number of high-quality measurements. So, moving on now to the implementation piece of things. One of the challenges that, again, we have in the R&D environment is bridging what I call the manufacturing gap. So, on the right-hand side here, I'm showing thermal scanning probe lithography, TSPL. You can get a tool for less than $1 million. It's a highly capable technology. It uses a heated AFM tip to draw nanoscale features in a thermal resist material. So you can get down to reliably feature sizes of 2 or 3 nanometers. It's great for probing the properties of nanowires and 2D materials and so on. But it is fundamentally not a manufacturable technique. In manufacturing for high-volume semiconductor production, we use high numerical aperture extreme ultraviolet lithography. You can have one of those tools for somewhere north of $300 million. It's a bargain. You need to build a specialized fab to accommodate it and so on. So it's really not something that a researcher is going to be able to get access to. So the challenge here is if I have a research lithography technology in my lab, how do I bridge that manufacturing gap? And I think here one of the critical pieces is having the manufacturing mindset. So when you think about the sort of the work that you're trying to do, there are ways of approaching it that can ease the transition into manufacturing or create an absolute manufacturing dead end. And I'm reminded of a story a friend of mine told me. He had a successful startup based around carbon nanotube electronics. And he was telling me about they were going to close their next large round of funding and had people that he was showing around his pilot manufacturing facility. And he got to a point and he said, well, here is where we use a chlorinated solvent to do this particular separation process. And at that point, the person he was with said, well, you can't use chlorinated solvents in manufacturing these days. And he said, he nearly dropped dead on the spot because he thought he'd lost the company. Fortunately, he was able to re-engineer that particular process and go forward, and as I say, be ultimately successful. But that's a perfect example of not having that tight linkage between the technology and the implementation. That was a critical, relatively trivial piece of knowledge that if he'd had early on, he would never have experienced that shock and alarm. But because he was working in a space where sort of things were somewhat disaggregated, that key piece of information hadn't got through to him. So we think of implementation in terms of manufacturing, but there's also a key implementation piece around intellectual property. And whenever I think of IP, I tend to wince because it invariably involves a somewhat painful discussion following that. I want to do 2 things on this slide. One is to just explain that intellectual property is actually a very broad concept, so we tend to think of it in terms of patents. The vast majority of intellectual property in the semiconductor industry is in the form of trade secrets. Those can be circuit designs, they can be process recipes, they can be process data, they can be what are called process design kits, which are an essential component of translating your conceptual design into a physical design, or algorithms. And the right intellectual property strategy can really enable innovation by allowing all the participants in the ecosystem to capture value. And that's a kind of a key point here, is that you want people to participate, but they're only going to do so if they can see something that's in it for them. And as time has gone on, companies have become a lot more sophisticated in how they think about intellectual property and have established things like trade secret registries, which allow trade secrets to be captured, securitized, monetized, and so on, and very importantly, from the government perspective, sort of transferred forward as acquisitions happen and so on. So I want to talk now about the market component, and again, trying to increase the pace of innovation. And this is perhaps one of the most difficult pieces for innovators to sort of not get hold of, but engage with. So if you've ever worked with startups, they spend a lot of time working with potential customers and frequently discovering that what they thought the market was not exactly what it is, and that requires them to pivot and change the direction that they're going in. And this is really a very high transaction cost part of the innovation cycle, because it involves engaging deeply with potential customers and sort of eventually getting that feedback Typically involves signing lots of NDAs and so on. So it's kind of a critical element here. Open innovation is one of the ways that you can imagine that market information can flow throughout the ecosystem. Open innovation does not mean giving stuff away for free. What it does do is allow companies to conduct very broad and distant searches, and that ultimately allows them to reduce risk. So I was talking with a colleague who works for a very large semiconductor company, and we were discussing this sort of concept, and he was saying, you know, we only have the resources to pursue maybe one technology option, and we're always really concerned that we might start down a path that turns out not to be optimal. And the challenge there is, you know, do I get to explore a large number of pathways simultaneously, which I do not have the resources as an individual company to do, but as a collective group, we can identify the optimum technology going forward. One of the key things here is that, again, everybody who's participating in this ecosystem has to see where they can capture value, and then the governance of the intellectual property that flows through these kind of environments is really important. And I'll give you just two quick examples. Companies that work actually building chips closely guard their process recipes and so on, their process design kits, but sometimes it might make sense to give those away actually for free. So if you're working right at the leading edge, those are the crown jewels, you'll hold on to them. If you're working at an older technology node, you might have more value if you open source your process design kit, because that's going to encourage people to design on your process and ultimately send orders to your particular fab. Another really interesting example I came across was Tesla, who said that they would allow people to use their intellectual property, not for free, but they would allow them to use it without fear of being sued in return for the same sort of thing. And the motivation there was trying to establish a market for EVs, and knowing that the more participants they had in helping establish that market, the faster and larger that market would grow, and the larger it would become. And then, you know, that's to the benefit of all the players in the system. All right, let me move along quickly here. I wanted to say a few words about ecosystem orchestration. So again, trying to get to that market piece where you encourage folks to share information as much as possible. Working in the area of advanced lithography, back in the 90s, it was clear that there was going to be a crisis. We were not going to have the technology necessary to make the most advanced chips. But Semitech, which was an industry organization working with an international technology roadmap for semiconductors, was able to orchestrate a tremendous effort around advanced lithography. The cartoon is of 4 competing technologies that we had at the time. And Semitech built consensus. The big industrial research labs worked on different technologies, exploring the different options, and ultimately the chip makers selected the winning technology there. In more recent years, an organization called IMEC has developed a really nice IP governance model. It's very flexible and allows partnerships between the research institution and different industrial partners to share intellectual property in a whole variety of different ways that really encourages participation in the ecosystem and allows that flow of information, particularly from the market to the technology development side of things. So I'll finish with just a couple of thoughts. Risk tolerance is key to innovation, and I know everybody likes to make fun of lawyers. They do, in fact, serve an important purpose. But I think many of us have had that experience where you go to a lawyer and you say, here's what I want to do, and they will list the whole set of risks that accompany that, and doing nothing is the least risky option. Whereas for an innovator, failing fast is the shortest path to success. I mean, you don't want to just keep failing, but again, you're trying to maximize that learning per dollar per hour. And a former boss of mine, actually, Masu, who's CTO at Applied Materials, said, the length of negotiation has to be shorter than a technology's useful life. And, it's important to be informed about risks, but it is also really important to say, all right, I understand, but I need to move forward here. And again, this is sort of part of my call to action is people get very hung up on intellectual property and risks and so on, but at some point you just have to say, all right, if we're going to make progress, we just have to do something here. Finally, I think, again, we're in a very exciting time. New technology is really creating a lot of opportunities. So this is just sort of a very notional plot of security versus accessibility versus innovation. And one of the questions here is, can I make information accessible but still maintain security? So an example that came to mind was, well, there are people who are working to understand variability in fab processes. But really, if I'm doing that, I might only need to understand what the distribution of variation looks like. Is it Gaussian? Does it have fat tails? Does it have thin tails? And so on. I don't really need access to the data. I just need access to information from that data. And there are technologies available in the secure cloud that would allow you to do that. So the combination of increasing compute power, cloud and secure cloud availability, the availability of very large data sets, and the ability to apply machine learning and AI to that is really opening up new opportunities to allow innovation to occur whilst still maintaining security and opening things up to a broad range of ecosystem participants. So let me conclude here. Again, my perspective is that we really need to think of ways of increasing the pace of innovation. And that means accelerating the cycles of learning that occur between technology, market, and implementation, broadly defined, by reducing the transaction costs of information flow between those three elements. And that really is what I would encourage everybody in this audience to think creatively about ways that we can do that, and ways of orchestrating ecosystems to encourage those free flows of information. So with that, thank you, and I'll take questions.
All right, do we have questions for our speaker? And remember to please come up to the microphone. There's a bit of a lead time while people walk.
Could you say a bit more about, you spoke about Semitech, and now in the present day they're standing up the National Semiconductor Technology Center, and any analogies you see there between the two constructs and the challenge of getting a bunch of companies together to do pre-competitive R&D, and how you think that might play out with the NSTC?
A good and difficult question. So the NSTC is still in the very early stages of formation, but one of the things that's been going on is looking very carefully at those governance models in terms of intellectual property and thinking about ways of leveraging new technology, particularly secure cloud, to allow companies to share information, but in a very careful and controlled way. So one of the beauties of having things reside in the cloud, for example, process design kits and all the design software, is that everything that you do with those things stays there. You can see who has access, who's doing what. It's never downloaded on premises and can then walk from that point. So a lot of that actually happened during the pandemic. Companies became used to sharing information that way. And I think that's a really exciting development because it allows a lot more people to participate in that sort of development and reduces the risk from the company perspective. So I think what we're seeing is that evolving, and I'm hoping that the NSTC sort of picks up on that sort of direction and also addresses sort of the IP governance piece, which is always very contentious, but, you know, if I could dream, it would be wonderful if there would be just a standard, you know, one-page NDA, take it or leave it, but if you want to participate, just sign this and we'll move on. So I hope that answers at least part of your question.
Just a quick follow-up on Semitech in particular. What do you think was important to the success of that with respect to getting these companies together to do pre-competitive work?
Part of it was sort of establishing industry consensus. And Semitech sort of made a transition fairly early on in its existence from sort of developing semiconductor technology to developing equipment technology. So it was in the interest of all the chip makers to get the equipment suppliers aligned and, you know, sort of moving along together, developing the technology for the next generation. And Semitech was actually very effective at doing that in conjunction with the International Technology Roadmap for Semiconductors, which just laid out, you know, 2 years from now, you will need a solution to this problem. And, you know, that went across the entire equipment supply chain and was immensely useful in sort of driving the industry cadence, you know, with a sort of new node every couple of years. So Semitech was a really useful forum and mechanism for achieving that.
All right, well, if there's no more questions, let's thank our speaker again. All right, and now we will hear from Dr. Tannenbaum from Sandia on the missing middle, national security, DOE labs, and technology.
Good morning. Thanks for having me, Lauren. I'm really happy to be here. This is my first March meeting. I'm an April meeting kind of guy, so I've learned an enormous amount at this particular week, so it's been great to be here. I'm going to talk today about a subset of the overall national laboratory ecosystem we have in this country. We'll talk about the research ecosystem in general, and then finally some novel applications of national security applications. I wanted to put this disclaimer up there because some people get a little antsy when I say some things out of turn. There are big generalizations in this talk. I also want to talk about U.S. government monopolies. So I've been thinking about this for about 15 years, and I can only come up with 2 real government monopolies. Anybody have any ideas on what a government monopoly might be? Nuclear weapons. Okay, there's one. That was the first one I came up with, and that's the field where I work in, so that was easy. And I'm glad that nuclear weapons are a monopoly because I don't want nuclear weapons being made for profit. But after about 10 years of thinking, I finally came up with the second one, and that is money, right? That's the other thing that the US government makes solely by itself, right? We don't have a private sector printing of money process. So what's interesting is that both of these, both money and nuclear weapons, have captive R&D, manufacturing, and disposal facilities that are operated either by or on behalf of the US government. Unfortunately, I'm not going to talk about money today. I'm going to talk about nuclear weapons and national security. So when we look at the enterprise across the United States of where we design, build, and maintain nuclear weapons, you can see the places on the map here. So this is at the end of the Cold War, so think late 80s, early 90s. You can see in purple are the R&D facilities, Los Alamos, right? We've all seen Oppenheimer by now. That was stood up then. In California, you've got Lawrence Livermore. Those are the two what we call nuclear explosive package laboratories or physics labs. And then you've got Sandia Labs. Sandia Labs was originally part of Los Alamos, but was spun off in 1949 because the folks at Los Alamos said, we don't want to do engineering. We want instead to focus on physics. And that's why there is both a Sandia in New Mexico and a Sandia in California to work with Lawrence Livermore there. Production facilities, and I really mean basic production, right? So the Hanford site, the sites in Ohio and Kentucky, those were focused on building plutonium and uranium, right? Uranium has to be enriched, plutonium has to be extracted from what's been run through a nuclear power plant. So doing some basic collection of materials there, and then the Savannah River site is involved in producing tritium, a key component of nuclear weapons. The assembly facilities, you can see there's one in Tennessee, there's Kansas City, there used to be one in Colorado called Rocky Flats, and then there's the Pantex plant in Texas. That one has made the news, unfortunately, in the last week or two because of the terrible wildfires that are going on. Those sites are involved in taking the things that are built elsewhere and converting them into actual nuclear weapons. And then finally, you see there in the lower part of Nevada, you have the Nevada test site, now known as the Nevada National Security Site. And that is where we did the bulk of our testing, but by no means all of it. So like I said, this is at the end of the Cold War. Now, some 30 years later, you'll notice that a fair number of the production sites have gone away. That's because we've stopped making new uranium and plutonium in this country. We have enough stockpiled to go for quite a long time. In addition, the Rocky Flats plant is closed. We don't make nuclear pits anymore there. The FBI rated them for bad work practices. We're now standing up that capability again at Savannah River and Los Alamos. So you'll notice, like I said, it's a little bit smaller than it used to be. These are all operated by the National Nuclear Security Administration, which is a semi-autonomous part of the Department of Energy. I say semi-autonomous because that's what it says in legislation. It's been around for 23 years now, and that semi-autonomous nature is still not 100% defined. So this is the national security enterprise of the Department of Energy. It's a subset of the overall Department of Energy lab complex. So if you look at the color chart there on the right side, you'll see that every major part of the Department of Energy has at least one laboratory. The Office of Science has the most. Right, they have 10 labs scattered across the country, from SLAC in California all the way to Brookhaven in New York. Not so much in the Midwest. We've got a couple around Chicago. You've got Ames in the middle of Iowa as well. NNSA, you'll notice, is concentrated in the Southwest. The first thing you notice is there are Sandias everywhere, and that's because there are Sandias everywhere. In addition to our main site in Albuquerque, we have another almost 2,000 people in California. We have a small site in southern New Mexico where we work on the storage of spent military nuclear waste. We've got folks actually just down the street here in Minneapolis. We've got people that work at Pantex in Texas. We even have a missile range that we run out of Hawaii. That's a hardship post. Not everyone gets to go there. We have a couple of folks up in Alaska that do climate change research, but they didn't warrant being listed on our homepage, so I didn't put them on this map as well. There's a lab in Idaho called the Idaho National Laboratory that works on nuclear power. Environmental management work happens at Savannah River in South Carolina. We have fossil energy work that happens in 3 locations across the country. That's the National Energy Technology Laboratory. That's principally working on the extractives industry. And then finally, in Colorado, there's NREL, the National Renewable Energy Laboratory, that is the part of the energy efficiency and renewable energy part of Department of Energy. So as I said, there are labs across the country that do all kinds of science. Most of these labs don't just do work for the organization that sponsors them. Sandia, for example, does work not just for NNSA, but also for the Office of Science and for the Office of Nuclear Energy, et cetera, et cetera, et cetera. Just as a highlight, those are the ones that were originally founded as part of the Manhattan Project, and you can see they're all still around and doing quite well. Let's turn now to the U.S. ecosystem, but before I do that, we should think a little bit about where does research happen, right? The speakers that we've heard so far have been from industry, and with a lot of focus from our friend at NIST on the industry part of what goes on there as well. We tend to think about industry and academia as being the major components of the research infrastructure in this country, but we can't forget the role that the DOE laboratories play. And actually there's a broader ecosystem of national laboratories beyond the Department of Energy as well. So we play a pretty key role there. Many of these laboratories are what are called FFRDCs, federally funded research and development centers. That's defined in the US Code and the federal acquisition regulations. It means we have a federal sponsor. It's one federal sponsor per FFRDC. It gives us access to privileged information. In our case, it's not just classified information, but it's pre-decisional information where the government hasn't yet decided what it wants to do. Sometimes we help them figure out what to do. Sometimes they just give us the information and we sit on it for a little bit. We're required to provide unbiased advice to government. We may not compete with industry, right? So even though, as I said earlier, there's this captive production facility, we can't compete with government, with industry on anything. That's great. Again, no private sector manufacturing of nuclear weapons, but there are other things where you might imagine the national laboratories could do things that industry can, but that's not the intent of us. We may not compete with industry. We steward capabilities on behalf of government, and the one that's at the bottom there has no assets except employees, right? So I'm an employee of this thing called NTES. It's an acronym. It's the LLC that runs Sandia National Laboratories. The only assets that NTES has are its employees. The buildings in which we work, the computers we use, my iPhone are all owned by the federal government, right? So the only assets that Sandia has are the actual employees. It's a very different model than you might expect in industry or in academia, but the intent is to make sure that we have access to the best government thinking, and we maintain these capabilities on behalf of government, right? There was a recognition when FFRDCs were first created that government salaries are not the same as industrial salaries, and if you want to have access to talent, you have to pay for it. And FFRDC salaries tend to be in the middle between government and academia and industry. There are 42 FFRDCs scattered across all of government. You can see the alphabet soup of federal agencies there. There are 16 that live within the Department of Energy. As I said, there are 17 DOE laboratories. One of those labs is a government-owned, government-operated facility. That's the one that works with the fossil fuel industry. Everything else is in FFRDC. All right, some definitions. The National Science Foundation has very specific definitions of research, basic research, applied research, and development. Basic research is what we call discovery science, right? It's when we're trying to do research to expand our knowledge without necessarily having a specific application in mind. Applied research, on the other hand, is when we are looking for the answer to a specific question. And then finally, there's development, which is where we convert knowledge into products. We talk about these things in other ways as well. So basic research is sometimes called curiosity-driven or discovery research. Applied research is sometimes called mission-driven research. And then development can also be called commercialization. We tend to think of research as being the domain of academia and commercialization as being the domain of industry. Not 100%. This is where the generalizations come in, but that's what how we tend to think of things. And if we look, so the National Science Foundation does some remarkable survey work on a whole host of things, including how much money is spent across the United States, both government and industry, and oh, by the way, by foundation as well, on research. And so this is the data from, I think this is 2021, where they surveyed not just how the government spent its money, but how industry spent its money, and they binned it into these basic, applied, and development categories. And if we look at this, right, we can see that academia there in the basic research category is green. The single largest category of basic research is academia. For applied research, you can see that now we've moved over to industry, and on the development side of things, industry is hands down, right? It's over 90% of the money spent there. It's also important to realize that although the pies there are the same size, they don't represent the same amount of money. Basic research was about $120 billion, applied research was about $140 billion, and development, right, commercialization, bringing product to market, $530 billion. Right? That's an enormous amount of money. We can take this, right, so this is looking at by sector how the money is spent, or rather by application how the money is spent. If we take it the other way, as we might expect, academia is the single largest place where we spend basic research money, and industry is the single largest place where we spend development money. If we look, though, at FFRDCs or the Department of Energy laboratories, you see this nice balance, though, where it's about 20% basic research, about 40% applied research, and about 40% development. This now gives us an ecosystem where we're covering that full spectrum of technology maturation in different ways than you see in academia and in industry. So if we take our DOE laboratories now, you can categorize them in all different kinds of ways. This is one where we've got discovery science on the vertical axis at the top and mission-driven research on the bottom. Left and right, we've got a single focus laboratory versus a multi-mission laboratory. And this is Benn's assortment of how the labs go. I know folks at all the laboratories. I don't think anybody would really argue with where I stuck things. You see Fermilab there in the upper left-hand corner. That's where I did my PhD research and my postdoc research. It does one thing, and it does it really well, right? It makes proton, and at the time it made anti-proton beams to do particle physics. Now it makes proton beams and neutrinos, but it does that one thing, and it does it really, really well. Other laboratories like Argonne or Oak Ridge they're funded by the Office of Science primarily. They tend to focus more on the discovery side of things. Those are more multi-mission laboratories. And then there in the lower right-hand corner, you see the 3 NNSA laboratories, Los Alamos, Lawrence Livermore, and Sandia. Los Alamos and Lawrence Livermore, they're basically going to be in about the same place. I would argue that Los Alamos does a bit more discovery science than Livermore does, but sort of up in the air. Sandia, on the other hand, we're an engineering laboratory. We have a lot of physicists on staff, but we are an engineering laboratory. Our main mission is to take the nuclear explosive package that is designed by Los Alamos and Lawrence Livermore and convert it into an actual nuclear weapon. There's a lot of engineering that has to go in to make that happen. So that's why we're all the way over there in that corner. So we're going to spend the rest of the time focusing on these 3 laboratories that are sponsored and funded primarily by NNSA. All right, so NNSA labs and technologies. What happens if you combine a deep understanding of national security needs, a unique, deep, and diverse set of R&D capabilities, and a captive specialized manufacturing complex? You can do some really remarkable things. So let's just start with thinking about some of the technologies that are in a nuclear weapon, right? All nuclear weapons contain plutonium and uranium. That's what makes them nuclear weapons. Are there other applications for plutonium and uranium? Plutonium, not so much. There's one non-nuclear weapon application right now, and that's to use it in thermoelectric generators for certain spacecraft, right? So for sending probes off to other planets and out into the galaxy, those are often powered by an isotope of plutonium. If you're in Europe, specifically in France, you might use mixed oxide fuels. The mixed oxide is a mixture of plutonium oxide and uranium oxide, so a little bit of plutonium gets used over there in their nuclear power facilities. But in general, the only reason to do anything with plutonium is for nuclear weapons. Uranium is pretty similar. Its primary application is in nuclear power. And that's a combination of power for electricity and power for the nuclear navy. It's also used in nuclear weapons. Tritium. Now, tritium is used in nuclear weapons to make them boomier. For a long time, it was in exit signs, and that's what made the exit sign glow. We've now switched to other technologies for that. But it turns out that tritium, as an isotope of hydrogen, right? Hydrogen is kind of nasty stuff. If you want to store it under high pressure in a gas bottle that you might want to use as a fuel source for your hydrogen-powered vehicle, you have to understand how the hydrogen is going to interact with that particular can. And hydrogen, being a small atom, it has the ability to burrow into the metal, and you get what's called hydrogen embrittlement. We had to understand that building gas bottles for nuclear weapons, and it turns out that knowledge is directly transferable to things that you might want to use for a hydrogen-based economy. So there's a nice little transition there. Radars, we'll talk more about radars in a moment. Nuclear weapons have radars in them because it's a cheap way to build an altimeter. You might imagine there are other applications for radars as well. Microelectronics, so far we're 3 for 3 in talks that include microelectronics. We'll talk more about that in a moment. Parachutes. If your nuclear weapon is a bomb, that means it's dropped out of an airplane. Chances are you don't want it to just go thud right into the earth. You want to slow it down a little bit. but you want to do it in a way, right? You want to, when you're sending your nuclear weapon off to war, you want to maximize the yield that it has and minimize its weight. And you want to have a very specific control over its moment of inertia and all those kind of things. So you pack your parachute in there really, really densely. Where else do we see parachutes? When we go to Mars, right? When we drop rovers on Mars, you have these parachutes that are quite complex as they deploy. Sandia was involved in helping NASA design some of those parachutes. Maintaining nuclear weapons also requires really exquisite modeling and simulation capabilities. For many years, the fastest computers on the planet were at the NNSA laboratories. Right now, Oak Ridge is a little bit ahead of us. They're one of the non-NNSA laboratories. We're standing up a new one at Lawrence Livermore that will come on relatively soon, and that title will come back to the NNSA. We also have a broad range of experimental facilities to do a whole host of experiments to make sure primarily that nuclear weapons will survive hostile environments. We can also use those facilities for other things as well. For example, fire. Suppose that the nuclear weapon is in a silo, the silo catches on fire, or it's on an airplane, the plane crashes, now you have a nuclear weapon that's been doused in jet fuel. You don't want it to go off. We have a flame test facility at Sandia where we can set things on fire and see what they do. It turns out that our understanding of flame can be applied to other things. For example, 20 years ago or so, we were considering becoming a major importer of natural gas. And there were concerns that, right, you bring your natural gas tanker across the ocean, you dock it, and now you have to transship the liquefied natural gas off that tanker. Is that a target for terrorism, right? Could a terrorist come by and try to blow up your LNG terminal? We filled a pool, a big pool at Sandia outside with liquefied natural gas and set it on fire. Okay, and it turned out that our understanding of large-scale flame wasn't as good as we thought it was. It did not agree with our models very well at all. But it gave us more data so we could go back and refine the models. We did the test again later and everything agreed. It also showed that liquefied natural gas, because it's liquefied and doesn't have oxygen in it, doesn't burn that particularly well. So that was a good answer. More recently, we used that same facility to work on whether or not Bakken crude oil. You may remember that there were a whole series of train wrecks with Bakken crude that caught on fire. And the question was, is there something special about Bakken crude that is more flammable than others? And so we did that test for the Department of Transportation, and the answer to that was no, it's not. So let's look at some of these more in detail. So as it happens, the laminar flow clean room that is critical to modern manufacturing for a whole host of things was invented at Sandia, not to produce microelectronics. It was originally invented to produce something called a strong link, which is a mechanical device that it's a safety device to prevent a nuclear weapon from going off before you want it to. But this guy, Willis Whitfield at Sandia, invented and then was issued the patent for the laminar flow clean room in the 1960s. When he presented his talk on this, the buzz was amazing because other people could see a huge number of applications for this particular technology. So, right, it revolutionized, actually it enabled the production of microelectronics manufacturing, it revolutionized pharmaceutical manufacturing, it created clean surgical operating rooms, it impacted R&D, space exploration, et cetera. So if we were smart, we would have licensed that to you all and we would be self-funding, but alas, that's not how things worked out. But this was quite an impressive feat on our part. We now at Sandia have our own silicon and compound semiconductor fabrication facilities ourselves. It's a nice place where we have a combination of an R&D facility and a production facility. Our needs for nuclear weapons are very different than the needs that commercial industry has or the consumers have for microelectronics. We play in quantum too. For many years, we made ion traps with funding from DARPA, and we sent ion traps all over the world so folks could begin to do experiments on quantum computing. The Human Genome Project, believe it or not, started at the NNSA laboratories. This was principally at Lawrence Livermore in California with work from Los Alamos and Lawrence Berkeley. One of our charges was to understand the impacts of radiation on human genetics. Part of this was trying to understand the long-term impacts on survivors of Hiroshima and Nagasaki, but it was also to understand what would happen if we fought a nuclear war and we sent our troops into combat where nuclear weapons were being used. So we built on that mission and combined experience with genetics and microbiology and robotics, et cetera, et cetera, et cetera, and that led to the automation of the gene sequencing. And so this led to the creation of the Human Genome Project in 1990, and then you can see the quote there from a book around the Joint Genome Institute, and we were able to automate the process in a way that led to a dramatic speed up in how many pairs could be sequenced in any given day. Now this was done in the year 2000, that's 23 years ago. At the time, they were doing 10 million pairs a day. Now that's about an hour's worth of work. So the pace of the acceleration of sequencing continues to increase. So another nice product that came out of the National Laboratories. Here's another great example. So when was the last time you saw a vacuum tube? Anybody? When was the last time you saw a vacuum tube? I was talking with my mom the other day. Yeah, exactly. So I was talking to my mom the other day. She's still got a CRT TV at home, and she's finally going to have to get rid of it. But that's like the last thing that's surviving in the wild right now. Nuclear weapons, a class of nuclear weapons, until about 3 years ago, still had vacuum tubes in them. Right? These were the radars. There was a recognition that we needed to replace those. But in the 80s, right, when we stopped manufacturing new nuclear weapons and stopped designing new radars, some folks at Sandia, because radar was one of our missions, said, well, could we take the radar that's vacuum tube based and put it on a chip instead? It turns out the answer is yes. And so what they did was they put it on a chip. Originally it was a big array, that's what you see there in the top middle picture. And we realized that we could, right, so now if it's on a chip as opposed to being in a vacuum tube, you can run it with lower voltage. It's going to be a lot more robust because microelectronics are more robust than vacuum tubes are. And now we said, oh, can we put it on a drone? And it turns out the answer is yes. You can put it small enough and have low enough power requirements that you can put a radar on a drone. Now, what can you do with radar? Yes, you can look for things in real time, but you can also use synthetic aperture radar that gives you the ability to look for change detection, meaning I fly over once, I take an image, I fly over again, I take an image of the same thing, I subtract the two, and I can look for differences. And that's what you see there in the lower right-hand picture, where you have the top inset picture is the before, the lower inset picture is the after, the large picture is the subtraction, and you can see very clearly tire tracks and what were parked cars along the way. Now, why would you want to use this? Well, this was deployed, right? So this is not a thing that, right? So we matured the technology, but then we licensed it to industry. Industry manufactured it, put it on the drones. These were then forward deployed in Iraq and Afghanistan. The resolution on these was good enough that we could look for improvised explosive devices. And the SAR technology that we put on the drones saved thousands of lives because we were able to say, there's something, not we, the military was able to say, there's something there, take a look at it before you send troops through there. And there was time and time again where we were able to defeat an ID by identifying where it was before it went off. More recently, these have been used for border control, right? There are lots of really remote places along the US border where you're not going to build a fence and you're not going to have manpower that can constantly be looking to see if anybody's trying to cross there. So instead, you can use SAR to see if anybody's tried to cross. This also can help, right? If you need to do search and rescue, you can do that with SAR as well. So quite an impressive technology that has a whole host of applications. We also get involved in crises sometimes. So 9/11. 9/11 happened, I was still a postdoc at the time, but there were plenty of folks at Sandia who were told, bring a sleeping bag, you're not going home for a while. It was looking at, first off, why did those buildings come down? Secondly, what else do we need to worry about? And how many of you, when you got on the airplane here, had to take off your shoes and take out your liquids and, all right, or were you all TSA pre-check? All right, so some of you had to take your liquids out, right? Don't hate me, the reason there's that limit of 3 ounces is because of Sandia. We blow stuff up, right? It's part of our mission, and we figured out that 3 ounces of explosive would be enough to knock a hole in an airplane window, so that's why that's that limit. Los Alamos, on the other hand, has been very deeply involved in building better screening technologies so they can tell what's in your luggage, and so you don't have to take everything out quite as much. Deepwater Horizon, there was a group, right, that was the oil rig in the Gulf of Mexico that blew up. We had folks on site there for about 40 days helping the Department of Energy and other folks figure out how much oil is coming out, which was an unknown question. Where's the oil going? And then how do we collect it and how do we cap it? When there was the big earthquake in Japan in 2011, that impacted the Fukushima Daiichi reactors there. As it happened, we had a perfect model of those reactors in silicon, and we could model what was going to happen on a minute-by-minute, hour-by-hour timescale. And so we were able to provide advice to the Japanese government on what they might be worried about. We had people on the ground in 24 hours for that one. Several of the U.S. DOE laboratories were involved in the Iran nuclear deal negotiations, where we were able to say, you know, if they have this, they can weaponize in this amount of time. If they have that, they'll be able to do these other things as well. So quite an important consultative role there as well. So here's my parting thought, which is the NNSA laboratories have a deep understanding of national security needs because we work in national security space. We have these truly impressive, diverse R&D capabilities, and we have manufacturing capability as well. That means that we can work in spaces where industry cannot, will not, or should not. And with that, I look forward to your questions.
All right, we will take questions for our speaker, and remember to please come down to the microphone since we are being live streamed and recorded.
Thank you, fascinating talk. Your laminar flow clean room example and the immense number of applications. Could you go back to that slide? I'd love to see so many applications, very amazing. Now, you made a passing remark that if the government had retained the patent and licensed it, it could have made a lot of money. So I have just a estimate question, how much? And this is a problem, you know, as taxpayers we should all be worried about and do something about, I think, or maybe, you know, I'd like your opinion on it, because it's not just this laminar flow clean room. Pharmaceuticals, they're made at NIH, it's all taxpayer money, and then the patents wind up in private industry, and medicines are very expensive, cause a lot of expenditure to the government, even though taxpayer, you know, it's a big problem, and I'm wondering, you know, whether you have an estimate of this particular thing or whether an estimate should be made of how much money the government could have made so we can move policy along. So, I mean, you know, it'd be in your benefit if you could be self-funded. So you get the drift of my question.
So it's a good question, and it's a really hard question. Another example is the World Wide Web, right? As a particle physicist, right? It was created so these huge collaborations could share data across the planet. But I think instead of the economic benefit that we've all received from having free access to the web, that's a hard question, and I don't know if there's actually an answer to it, right? What technology should the government license to industry versus for some fee versus for free? I don't know the answer to that question.
Yeah, but what should we try to find an answer? So World Wide Web is a great contrary example. Contrary to this. So this has been licensed, make a lot of money, World Wide Web, free, lots of public benefits. So maybe we should develop some metrics, we should do some study. Something should be done rather than, oh, it's just the way things are.
Well, so, you know, each of the laboratories will do an annual economic impact on their state and on their region, and they're often quite significant. But I don't know if we've gone back far enough to really look at what are the economic impacts of something like the laminar flow clean room.
I read a lot of Sandia reports, and I look forward one day to reading a report on this.
Okay.
Thank you.
Yep.
Good morning, thank you. So you had two photos at the beginning, at the end of the Cold War and now, laboratories and facilities that produce nuclear weapons. You said you had a lot fewer. Tell us about the Sentinel program, where you're intending to actually, as far as I can see, completely upgrade the nuclear weapons that will go in the ICBMs that sit in the middle of the country. Could you tell me, are you going to be working on the Sentinel program?
So the Sentinel program, for the folks who don't know, is the program to update, to modernize the intercontinental ballistic missiles that we use to hold some fraction of our nuclear weapons. That's a Department of Defense and a Department of Air Force activity, and so the NNSA laboratories are not involved in that, except in to help define the interface between the weapon and the delivery system itself.
So who is designing the weapons?
The weapons, that work is being done at Los Alamos, Livermore, and Sandia. But the weapon itself is separate from the delivery system.
Right.
The delivery system is done by the Department of Defense, right? So in this country, we said we're going to split nuclear weapons, so there's civilian control of nuclear weapons, which includes the design and the manufacturing, and the military will be responsible for getting them to wherever it is they need to go.
Right, so that involves a lot of commercial companies such as Lockheed Martin, who actually design and help you make the missile that actually delivers the nuclear weapon. So at the beginning you tried to make out that there was not much commercial stuff involved, but in fact there's a great deal of commercial stuff involved in nuclear weapons because of their delivery systems. The delivery systems are made by commercial companies.
Correct, but the delivery systems have other applications as well, right? Commercial space is a big thing, so, yeah.
Hello. I have a similar, I guess, licensing question, but this time about present-day systems. So I guess we learned from our mistakes, and as a lab employee in the DOE complex, when I signed on as an employee, I signed a piece of paper that said any inventions that I create at the lab are the property of the lab, and if I want to go and create a company with the invention that I create, I have to license that intellectual property from the lab, and it has to be approved by the DOE. So in this current day and age, as your talk implies that the labs are kind of like the middle ground where we're shepherding new technologies to industry, and a lot of money is being pumped into the labs so that they can make this very nice new technology that can be in turn lift up the U.S. economy. How long do you think it takes from a person creating the technology and saying, I want to license this, to that being a package being put together and then approved by the DOE? How long does that take?
It depends. It's not a satisfactory answer.
How long is reasonable?
There's, I mean, some things never get licensed. Some things we can license on a postcard, right? We've specifically set up some of our things to be licensed that easily. Most of the laboratories have an entrepreneurial leave program where if you've been working on a technology and you want to spend some time seeing if you can actually bring that to market, you can separate from the laboratory for 2 or 3 years, licensing essentially your own technology, and then if it doesn't work out, you still have a job. If it does work out, great, go do your stuff. It might take a year, it might take 6 months. It just depends on the technology and who you know and how fast you can move things along.
Okay, so I guess on the question of how fast you can move things along, if it's taking about a year, is this a good space that we can improve on to compete with China? If it's taking a year to get? So
I think the bigger problem is, right, in the basic research community and some of the applied research community, we do a lot of work at very low technology readiness levels. And industry is interested in things at very high technology readiness level. And it's that space in the middle, called the Valley of Death, where we need more people willing to work and more money willing to work. And overall, that if we had more investment there in general, I think we'd be better off. There is a lot of IP that is locked up at the DOE laboratories, but it's not, someone's got to be willing to commercialize it, and it's not really the role of the laboratories to do that in most cases.
But if there is someone who's willing to commercialize it and they have funding, but they need IP and it takes a year, that's kind of the root of my question.
So you're asking, are there ways that we can speed up the licensing process?
Yes.
And I don't have
this kind of very fast-paced.
Yeah, I don't have an answer for that.
Okay, so thank you for answering that.
All right, be super quick. You got this.
This will be, okay. How much does the constraint of not being able to compete with industry actually impact what is done in the labs?
I would say not at all, right? Because It means that when we think about where we want to do work, we know that some spaces are off limits and we just don't even go there. Or we might say early on, we know at some point we're going to transition this to industry. And so early on, we're going to develop relationships with that industrial partner so that they can take over the technology and then bring it to market, et cetera. And the SAR is a great example of that, where we knew what we were doing and we know we're never going to commercialize this. So let's identify who the commercial partners are pretty early on.
Thank you.
Mm-hmm.
All right, let's thank our speaker. All right, and our next speaker is Dr. Anzelc, and she will be talking to us about AI and data innovation, innovating in constrained environments.
So, hi everyone. I'm really happy to be here. I have been at March and April meeting before, and I always like coming back. So I'm going to tell you a little bit about my background, and actually I'm so glad that Benn was just before me, because I've got a couple of personal anecdotes about how national labs influenced me in my career. So I want to give you a little bit of background to set the stage for what I'm going to talk about and how it's a bit different than some of the other speakers. So I did my bachelor's in physics at Loyola University Chicago, and then I went to Northwestern and did both my master's and PhD in physics and astronomy. Through that process, I did a number of internships at Department of Energy National Labs when I was an undergrad. So I worked at Fermilab in their high energy particle division. I worked at Argonne, both at APS, the synchrotron, and in their HEP division as well. And that's really what got me interested in pursuing the PhD in physics and interest in a research career. What I learned and why I pivoted was because two things. One was I was doing basic science research. So I was studying what happened nanoseconds after the Big Bang, which was super interesting, but there's only like 300 or 400 people in the world that care about it. And any material impacts to society of what we were learning and studying take decades to measure. So for example, MRI machines that are in every hospital today are in part because of accelerator research work that was done at Fermilab many decades ago. So I was interested in, can I do work that is a little more applied, where the timeline to impact is measured in years or months rather than in decades. So I ended up in the insurance industry. Now I can tell you, nobody grows up saying, I want to be an insurance person when I grow up. So most everybody who ends up in insurance sort of falls into it somehow. The problems, though, are fascinating, they're complicated, they're challenging, and so I ended up staying in that sector for a decade. So I worked at 4 different insurance carriers. I did personal lines like car and home, the things that you and I buy as consumers. I did commercial lines, which is, insuring this property as an example. And I did specialty lines and reinsurance. So I kind of saw the whole space. And then I pivoted again, and I was recruited into Spencer Stuart, which is an executive search firm. Executive search is recruiting headhunters, so they're middlemen between companies that want to hire senior executives and the candidates that are out there in the marketplace. Executive search firms also do work with universities and some government institutions for very senior level positions. So presidents of universities, deans of schools, things like that. So you may have interacted with a search firm at some point through some of your work. And then for the past 1.5 years or so, I've been consulting with companies on data and AI. And so a little bit about the context around the types of companies. So the insurance industry is very highly regulated. So I worked at 4 highly regulated companies. I have worked at 4 global companies. So that's Zurich, AXA, Spencer Stewart, and the consulting I do now. I've worked at companies that were headquartered in 3 different countries. So 3 headquartered in the US, 1 headquartered in Switzerland, that's Zurich, and 1 headquartered in Bermuda. That's Axis Capital. Bermuda seems weird, but Bermuda is actually a common headquarter location for certain types of insurance companies. If you go to Bermuda, it's everybody's in insurance down there. And then the kinds of teams that I have worked with. So I've worked at companies where everything was in person and all the people I worked with were in physical locations, either with me or in other field offices. I've worked in situations that were hybrid, sometime in the office, sometime at home. I've worked in situations that were fully remote and where things were global. So I've managed teams who sat in other countries as well as in other locations in the US. So I'm going to set that because we're going to talk about some of the constraints that come into the private sector. So the big ones, and there are more than this, but I wanted to focus on just a handful. So in the upper left, the picture of the globe, so this is about regulation. So regulations vary by industry and by geography. So for the insurance industry, as an example, when we talk about like auto insurance for our own cars, that is regulated in the United States at a state level. So there are 50 different departments of insurance that individually regulate the insurance for their state. There's a lot of overlap in the regulations, but there are nuances and differences. So even if you only operate in the United States, you have to manage across many different versions of regulation to launch a product like auto insurance that can service the whole country. And then of course globally, right, there's lots of differences. And this is sort of across many types of use cases and industries as well. So in human capital, for example, there are rules. For example, in the United States, the Equal Opportunity Employment Commission says you cannot make employment decisions based on protected class, race, gender, ethnicity, religion, things like that. In some countries, you are not allowed to even capture information about some of those characteristics. So there's a wide range, again, of even what data you can collect and what data you can use for what purpose, again, varying by geography, by industry, and so on. In the middle top is about people. So your talent pools for a private sector company, if you're doing things in innovation around AI, the talent pools vary widely, again, by geography, and again, depending upon the use case. Insurance is a fairly complicated industry to understand, in part because it's so highly regulated. So it's hard sometimes to bring in lots of people who they might know AI, but they don't know insurance at all. So you've got to find the right kind of mix of people to do things as well. Data security in the upper right is another one. So both from a company's own perspective about how they want to secure data and how they want to manage how data moves across borders, there are also laws and regulations around that. So GDPR, the privacy law in Europe is an example. California has a Privacy Act, right? There are other laws and regulations around this as well. And then there are also contractual obligations that companies have around this, where a company might say, you can do work with us, but we don't want our information used for any other purposes than the very narrow project definition of the work we're doing with you, right? So there are constraints on how you can use data in other ways too. In the bottom left, budget. Money is always a problem. There is never enough money to do all the things you want to do. There's never enough time to do the things you want to do. There are never enough people to do the things you want to do. So that is a continual constraint. And obviously, depending upon what's going on in the broader market and how the company is doing, that can be a much tighter constraint sometimes. And then in the lower right is operations. So when companies operate globally, that can also add additional challenge. Just things work differently in different parts of the world. And an example for the recruiting industry, labor markets are fundamentally different in different places. So even if you're not talking about regulation differences, people in the United States tend to move jobs fairly often, right, every handful of years on average. People in, say, France don't. They tend to stick with a job for a very long period of time. So the available labor pool to do the work you're trying to do is different in France than it is in the United States. So some examples of how this shows up. So I'll give both some examples from insurance and from the human capital space. So this was a project that we did at one of the companies I worked at, looking at workers' compensation and the potential for fraud. Now, the historical way that you identify potential fraud in workers' compensation is somebody says, they call their employer and say, I hurt my back at work yesterday. I'm really badly injured. I can't come in. My doctor says I have to take 3 months off. If there's a suspicion of fraud, there are people who are generally ex-military or ex-law enforcement, hired as investigators, who might follow that person around and do surveillance and come back and say, actually, that person played 36 holes of golf on Saturday. Clearly their back isn't that badly injured, right? So that's sort of a historical example of how it works. But that's very narrow, right? That's looking at the single individual who's making that claim, that worker, and how they might be, whether or not they might be doing something that's fraudulent. What we were doing was instead saying, we don't want to look at the workers, we want to look at the system of providers and care and see if there might be indicators of fraud at that level. So much more about broad-scale pattern recognition than about surveilling a single individual. So what we're doing here is we're following a number of workers. I don't know why they all have ties, why they're all men. I should change these graphics. But if you look at the way that they go through care, one sees Dr. A, then gets referred to a specialist in Dr. B, then they have to have a follow-up with Dr. C, and so on. So you can build this pattern of care for all these workers, and then what you can do is convert it into a network analysis and say, how are these doctors interconnected to each other? And so in this example, we're seeing Dr. A at the center, who has the most interaction with Dr. B, right, where that line is thickest. So the two of them do a lot of work together, right? They end up with a lot of the same patients. Then what you can do is start folding in other kinds of data. So the insurance industry keeps data on who has been labeled as a fraudulent provider in some way, right? So the sector actually helps each other out in a few use cases to share very specific kinds of information. So here you can start folding in some of that information along with court records and other things, and you can find some super interesting stuff. So in the middle of the top is, I know the letters are hard to see, but E, that sort of yellow box there, is very closely tied to a doctor in gray, but that doctor is currently in jail. This doesn't mean that Dr. E is doing anything fraudulent, but it does make you wonder, right? They're also connected to someone who has been accused of writing unauthorized prescriptions. So now there's two potential indicators, right? They're connected to two people who have been doing things that are wrong. So you can put together maps like this to then say, okay, are there some areas where we see real outliers, where we see areas of concern, and now do we want to provide a different type of investigative follow-up to those to investigate further to actually determine if there might be fraud happening, right, at the provider level, not at the individual worker level. So in this case, right, for workers' compensation, I've got the little graphics in the upper right. So workers' compensation is a highly regulated coverage, right? There's a ton of rules about the way you can price for this insurance and very strict rules about how you pay out work comp claims. They have to be done the same way everywhere. So if you injure your hand in a particular way that prevents you from typing at your job, there is a payout for that is standard, right? But again, it's in the United States, it's regulated at an individual state level. So very tightly constrained around the regulations. Data security is obviously a clear constraint here because you're talking about healthcare information, right? This is very sensitive information about people. This is personally identifiable. This is stuff that has to follow HIPAA regulations in the United States, right? You have to be very, very careful about how you're using this data and who has access to it. And then again, budget is always a concern. So some of what we were doing here was actually finding ways to use unstructured data, so things from medical records and notes from the claims professionals as they were helping the worker through their injury, and extracting information out of that text to then help aid in this analysis. And if you can build something that works and you can do that at scale, you need upfront labor to build all that, but less labor to maintain it over time, right? And if you can identify and prosecute a couple of fraudulent providers through this, you may be able to save the company significant amounts of money where you pay for the project itself, right, over time. So in executive search, so sort of this recruiting space, this is one where, as I mentioned, that global operations, right, the fact that labor markets are different in different parts of the world is a very significant constraint and adds a lot of complexity to trying to solve some of these problems. Again, data security is really important. So both because you have lots of information on people's career profiles, you might have as well, if, for example, the search firm is hired to replace a CEO of a publicly traded company, the current CEO doesn't know that, nor do any of the stockholders, right? So you're talking about material non-public information that has the potential to impact the stock price of the company and the livelihoods of other individuals, and that information has to be very carefully protected. And then again, budget is always a concern, capacity is a concern. It's hard to solve some of these really complex problems on, you're always trying to find a way to do it that is as cheap as possible, as fast as possible, while still providing value to the company. So some of the things we were doing here was around outreach communication. So in executive search, this is a different kind of industry than the way you and I have applied for jobs most of our careers. The job for that public company CEO is never going to be posted publicly. So how would you ever find out about it? Well, a search firm has to reach out to you. So they're always doing this outreach to potential candidates, but those candidates are what are called passive. They're not actively applying to a job. There are no jobs to apply to, right? It's this cold outreach to say, hey, I have a job. I think you might be interested. I think you might be a good fit. Let's have a conversation about it. But executives are very busy, so there's a lot of communications that go out and then never get a response. So what we were trying to do is to give them some augmented writing tools around how could they craft communication that would be statistically more likely to lead to a response. And how could they craft that communication in a way that was using language as inclusive as possible, because the historical way that historically the people that have held senior executive positions in companies has been overwhelmingly white and male, certainly in the United States, right? So very homogeneous historical data. So how could you use inclusive language to try to increase the likelihood, not just of responses in general, but to get more responses from people who are from traditionally underrepresented groups? We also did work around the specific teams assigned to work on some of these projects. So how do their collaboration patterns and their own communication patterns influence or are correlated to how well the search is conducted and how quickly it finishes? And companies like Spencer Stuart care about how fast a search happens, how quickly they put somebody in the role, because the faster they can do that, the faster they can take on another search opportunity and add more revenue to the company. Right, so the more volume they can do, the more money they make. And then we were also looking, this obviously is an industry that has lots and lots of unstructured data. So resumes, comments, job descriptions, right, all of those sorts of things. So a lot of work going on there. And then we were doing work as well in a candidate recommender system. Again, this idea of can we recommend people who have skills and experiences that are really related to the success that's needed for the job, and can we surface those people in a faster way, but also in a way that it is more fair and reduces some of the potential for bias to come into the process. We also, because of kind of budget constraints and even talent constraints, this was a team where we had a very small team at Spencer Stuart, sort of employees and contractors, and so we were looking for ways to increase our capacity to take on additional projects. And so one of the ways we could do that was through academic partnerships, and we did a couple of these. The other partner I'm not allowed to name, but we did a project with NYU with a group of undergraduate students who were helping find tools and ways to extract information from external data sources about executives. So many of the demographic kinds of data that we would want to know, like gender, ethnicity, LGBTQ status, we either need to use self-reported information. Again, it depends on the country and its rules of where that candidate sits and where they have citizenship. But we also want to use self-reported information from reliable news sources, as an example. So for example, Tim Cook, the CEO of Apple, has been very public about his being a member of the LGBTQ community, right? He said that in multiple large public forums, has been quoted in sources like the Wall Street Journal and Fortune, right? Reliable sources that you can pull from. So that's what the NYU students were helping us do, was to say, are there tools and ways that we can extract additional information? Sometimes companies also put that kind of information into their public filings with the SEC, with the Security and Exchange Commission if they're a publicly traded company, so we could also extract some of that text out of those documents to try to add to the demographic information we had on people. So this was a way to achieve more of the projects that we were looking to do, but without needing to hire additional staff, right? So a very low cost, no cost solution, but that let us take on additional work. So sometimes innovation can't solve your problems. And so this is a list of, as of 2016, so this list has probably changed a little bit, but the largest man-made insured losses globally. These are in US dollars, in billions of dollars, at 2015 dollars. And you can see that, right, the 9/11 attacks is the top. There was an explosion in the UK in the 80s that is the second most expensive. The third most expensive happened in 2015 in China, and this is the Tianjin port explosion. So I bring this up because I was actually working at Zurich Insurance when this port explosion happened. And one of the things that Zurich insured was car dealerships in the US. So they were at the time, I believe, the largest insurer of car dealerships. So when you think about a car dealership, you think about the picture on the left, right? You think about a huge parking lot, hundreds of cars, a couple of, single-story buildings, right? That's kind of what you think of. So normally when insurers insure something like a car dealership, they're worried about things like theft, and they're worried in places like Oklahoma about hail damage, right? If there's a bad hailstorm in Oklahoma on a car dealership lot, you've totaled hundreds and hundreds of cars, right? That's a huge loss for an insurance company. So those are the kinds of risks that they normally think about. What Zurich did not fully understand before the port explosion was that their insurance covered those vehicles upstream in the supply chain. So they insured them all the way back to some part of coming off of the production line. And what that meant was that many cars that were manufactured and finalized for delivery in China then went to a port and sat in big containers at the port, and then were put on ships and transported to the US. The Tianjin explosion happened, destroying tons of things, and a number of lives were lost, right? So this was a really big event that happened. But what Zurich had failed to do was to sort of work through the thinking of how might that data of that exposure to potential loss, right, that risk of having to pay out for claims, how does that exist other than on the physical sort of car dealership lot or when cars are being transported across interstates in the US? So they misunderstood, and this resulted in $275 million of losses for Zurich alone. I can tell you everybody's bonuses were impacted that year. and Zurich abandoned a proposal to make an acquisition of another company. So they had been in talks and were seriously working towards the acquisition of another firm, and effectively they couldn't afford to do it because they had this huge loss that they had to pay out. So when you're talking about innovation and how to do it within all of these different constraints, it's also, in my opinion, very important to consider all the different aspects of the context of the company that you're working in. So if you're in growth mode, you might have a greater appetite for innovation. You might be more willing to take risks, to try things that might not work, because your growth might be able to sustain that if you have a number of failures through that. If you're in a company where you're just looking to keep a well-oiled machine running, right? If the company's been successful for a long period of time, generally it's a little harder to innovate because most people don't want to disrupt the status quo, the sort of like if it's not broken, don't fix it type mentality. And then if you're actually going through an active crisis as a company, this can be kind of one or there can be opportunities for both. So there can be some real opportunities to innovate because people are trying to desperately, very quickly turn things around, and they're looking for ideas that will work and will work fast. So there's an opportunity for innovation there, but it has to be innovation tied to helping that company get out of the crisis, right? And then, of course, all of the time when we're doing this work, we have to tie what we're doing to the organization's goals. What is the business trying to achieve, and how does this work align to that? Because if it's not closely aligned, it's very difficult both to get buy-in from leadership at the organization, but it's also hard to get budget and people and support and all of those other things. And then sometimes looking at what else is in flight at the company. So I've been at places where they went through enormous change all at once. So the start of the pandemic might be a good example, right? Suddenly your IT team is freaking out because people don't know how to log into their computers from home and nobody's got a monitor and right, all of this craziness. Probably not the time to start a new innovative research project that might lead to something, right? There's just not the attention span, and there's too many other things going on at the company at the same time. And then also looking at what else is planned in the upcoming time frame, because that might help you, again, kind of tailor your innovation approach to what the company's going through. So to sort of sum up some of this, really around really coming back to the what problems are you trying to solve, and I know a few other speakers had kind of highlighted that as well, so I just want to reiterate that of starting with what are the outcomes you're trying to achieve, what are the goals, what are the problems you're really trying to solve, and then also asking, is a simpler solution good enough? So many times in organizations where I've been on teams doing AI work, I would say many, many times the answer is not to build an AI tool. The answer is maybe training is needed because there's already a tool that exists, just nobody knows it exists. Maybe you just need some simple algebra to solve the problem to a level that's sufficient. And then really considering what can you do with the data and technology you already have. So rather than launching some large new thing to go out and do something totally different or buy a whole bunch of data that you don't have, are there things you can do to innovate and create value from what you already have today? And then, as I said, what should you do given what else is going on in the organization, including how much change people can handle. There's only so much we can change at a time. People are generally dislike change, all of us. And so there's only so much we can ask people to do differently at any given point in time. And then, of course, companies also want to consider what their competitors are doing and what fits within their budgets and their scope. The other part, and I know one of the other speakers mentioned this too, it's really important to have cross-functional expertise help think through things when you're doing some of your project strategy. So this includes people from legal, compliance, and privacy teams because of those regulation constraints, because of those compliance issues. Your security and architecture teams, how do you continue to protect data in ways that make sense? The actual data owners, can you access the data? Can you use it? Are you allowed to do things with it that you want to do? And then the actual business unit owners, right? Making sure you're really aligned to them because you don't want to build something that you believe to be useful, but then nobody uses it when you're done, right? So you want those people included up front. So I think with all of this, it's really about using some of those questions to think through what are the ways you can innovate within the constraints you have. And I have continually found throughout my career really fun, interesting, challenging work that also adds to the value of the organization, despite the fact that every organization I have operated under many of these constraints. So I think sometimes we think about constrained problems as being a disadvantage, that it makes it too hard to do what we're trying to do. I think of it as opportunity to be creative and innovative and find ways to do things differently while also fitting within all of these different constraints. So to me, that's actually one of the things I love most about working in the private sector is working on constrained problems, because it's harder and it's more interesting, and frankly, I think it's a lot more fun. So thank you, everybody.
Thank you. And now we'll take questions from the audience for our speaker, and remember to please come up to the microphone.
Hi, thank you for the really interesting talk. I had I guess maybe sort of specific question about how you use AI to identify executive candidates. So you mentioned that it could be used as a tool to decrease human bias, but I think we've all probably read some news stories about how bias can often be baked into these models, and they can use little tricks like home zip code and stuff to code for things like race that you intentionally tell them to exclude. So I was wondering if you have like training strategies to avoid those sorts of issues.
Yeah, so trying to remove bias from the hiring process is an incredibly difficult problem. And in my view, you have to be thoughtful about how to do that from the design, right? From the sort of idea, inception, and design of the solution that you're trying to create. So unfortunately, I get frustrated because I feel like there are tools where people get sort of spun up in this AI hype cycle, and they're like, oh, we need to launch a thing. And you're like, but are you just encoding all the biases that have already, right? If you're just automating what exists today, you are encoding bias, right? So you don't want to do that. You want to try to find ways to reduce the level of bias so that you're actually making things better. It's really, really hard to do. So some of the ways are to try to, so what we were doing was actually trying to get down to what are the skills and experiences that are correlated to the people who make it through multiple steps in the process. And then we were checking to see if what we were uncovering in those things that were correlated to that move through the process, if those were really just proxies for things like gender and ethnicity, right? So if you think of like extreme examples, if you think of lacrosse as a sport, you think of white people, right? And that's for good reason. Overwhelmingly, lacrosse players are white. So if you're seeing something like that show up, right, as a silly example, but if you're looking at hobbies on resumes and stuff like that, you have to be very careful about, right, sort of trying to really dig in and investigate. It's also very difficult. We did some work where we were looking at resumes, because there's a lot of research around, like if you look up the Heidi Howard study, super fascinating, just Google it, of how people's unconscious bias shows up even on the same credentials. We were trying to remove gendered information from resumes and sort of de-identify them as much as possible, almost to the point where we made the resumes useless, right? So really pulling down the level of information. We could still predict with better than random accuracy, right? Something above 50%, the gender of the person whose resume it was, right? Which makes me want to go out and have a man write my resume, because that would probably, right, to just take all the credentials, but I want a dude to write it, because then I will be more successful in the process. So I know I'm not exactly giving you like a black and white answer, but it's a very hard problem. And I think if you're looking at trying to use tools in your organization, that due diligence before you start using a vendor tool is super critical, especially if you only operate in a certain industry or a certain geography. That doesn't mean the tool will work when you move it outside of its training data set.
And
right.
It sounds like a pretty critical component is maintaining like human in the loop during training, where you're looking at what correlations the model
Yes.
has discovered in testing to make sure.
Yes, so we were both doing that ourselves. We were doing a lot of the analysis on the data science team itself, but then we were also talking to our recruiter partners and saying like, hey, we keep seeing this thing pop up. Like, does this make sense to you? Right? What's your reaction to why we might be seeing that? And sometimes we were misunderstanding what the data meant, right? So it was super useful for that. Sometimes it was, you know, about like a common industry characteristic, and we were like, oh, okay, now that helps us because now we can actually code that into some of that initial filtering, because if that's a critical, right, identifier, we want to make sure we're including that. So a lot of that, it's very, very iterative, and with, again, with that cross-functional group. Yeah.
Thank you.
Yeah.
We do have time for one last one.
Hi, thanks for the talk. My question is around like sort of data security. I know with AI, it sort of inherently needs a lot of data, a lot of sensitive data. You mentioned HIPAA and, you know, with resume and stuff. So I just was wondering about, you could talk a little about maybe the ethics or the challenges or things that sort of surround data security and the ways that you approach that.
Yeah, so that is also a big question, so I'll do my best to answer, but I'm always happy to have a follow-up. So for the data sources that include very sensitive information, much of that is about making them accessible and visible only to a really small number of people who actually need it for the work. So as an example, in one of my jobs in an insurance company, we needed to pull credit reports on lots of people, and we needed to use people's social security numbers in order to do that. There were, I think, 3 of us on the team who had access to social security number data. We had to sign a separate contract with the organization, you know, swearing on our mother's lives that we would not misuse this data in any way. That access was only given for a short period of time, and then that access was removed once the initial project was over. And then once we had structured the data the right way, where you didn't have social security number in it anymore, then you could make the data available to a bigger team, right, a project team to support. So that's one way, is controlling access and who can see into it. We did that at Spencer Stuart as well, where actually even the IT team who set up the data pipelines for us couldn't see the data. So we could see it. There were only 2 of us for one data set we had, but even the architecture teams within our own organization couldn't see into the boxes that they made for us to put the data. The other piece is around when you're talking about data security, the whole generative AI explosion has a whole nother set of complexities associated with it, because there's been a fair amount of stuff published and in the news about ways you can sort of trick the tools into revealing information that they're not supposed to reveal, right? So either revealing actual input data or source information, or in other ways using sort of personally identifiable or sensitive information that was not sort of the core intention of the tool, but because they, in my view, my guess is most of them weren't designed with that data security in mind from the beginning, right? So it goes back to that start up front with what are you trying to accomplish and what are the constraints you have to work within, because that's a whole lot easier to solve before you build it than it is to take something like ChatGPT and try to now re-engineer or put constraints around it so that you can't trick it into giving you things it shouldn't be giving you. So hopefully that helps a bit. I am also reachable. My contact information's there, so if other people have questions or you want to talk about careers in the private sector at any point, I'm happy to talk. So thank you very much.
Thank you. Let's thank our speaker. All right, and our next and final speaker to this really wonderful session is Dr. Virgo from the Department of Defense, and he will be talking about Pentagon physics.
Good morning, everyone. Now, my current job at the Pentagon is directing a part of an organization called the Analysis Working Group. Now, this group, much like the physics community, you work really hard to make sure that your research is transparent, robust, and collaborative. the Analysis Working Group, AWG, what we do with defense analysis is to also make sure that that analytic work is transparent, robust, and available to support senior leader strategic decisions. So major decisions on defense programs. Dr. Tannenbaum talked about the fact that NNSA and DOE, they build the nuclear weapons. In the Defense Department, we have to figure out what is the right balance between the nuclear triad, the balance between the weapons that are based air, land, and sea. So major strategic decisions that come up. And if you want to know more about the AWG, we are established in US law. You can look us up to get some details. But that's not where I want to start this talk today. Instead, I want to take you back and talk about some fundamental physics. DoD funded fundamental physics that I actually did many years ago as a young postdoc. So I'm actually a physical chemist with a specialty in laser spectroscopy. And so I'm going to start with this figure on the left and talk about some work that was funded by the Air Force Office of Scientific Research, AFOSR, many years ago at MIT, where I did a postdoc in Bob Field's group in the chemistry department. This work was done back when we published in the Journal of Physical Chemistry. It resulted in a feature article, so we got our artwork on the cover of this particular issue of the journal. But let's dig into some of the details. So think back to your early chemistry lessons. The figure on the left-hand side here, we're looking at a potential energy diagram, and we're talking about a molecule that is fairly simple, at least on the surface, acetylene, C2H2. So if you look at that figure, the ground electronic state of the molecule, that S naught, acetylene is a simple linear molecule. But one thing you learn in chemistry is that when you have an excited molecule in an excited electronic state, all the dynamics, the chemistry, the basic properties of that molecule can be very different, profoundly different from that same molecule in its ground electronic state. And if you look at the top part of that chart, the excited electronic state, S1, there are actually two very different geometries for the molecule. So when we do laser spectroscopy, you can use laser techniques. I use pulse lasers to excite the acetylene molecule in the gas phase from the ground state to this excited state, S1. It's either transbent or cisbent. And there are a number of different structures involved here as you kind of watch along this reaction pathway. All the way on the left, there's a vanillidine structure where magically somehow both of the hydrogen atoms end up on one side of the molecule. There are many different structures involved. So this brings up some fundamental questions. When you have a molecule in an excited electronic state, what can happen to it? How does it give up that energy? So what are the pathways for the decay of that energy from that excited electronic state? And do some excited electronic states give up their energy more readily than others? So these are the fundamental questions we were looking to solve using laser spectroscopy. And like I said, this work was published in partnership with Bob Field's lab and my partner Kyle Benninger many years ago. So it's your photon exciting to the excited electronic state. Now, we need to dig a little bit deeper into this. So if you look at most molecules, most stable molecules anyway, actually the lowest energy excited electronic state of most stable molecules is actually a triplet. So if you look at this diagram on the left with the blue box, in chemistry you talk about a pi to pi star transition. You have singlets and triplets. The difference just depends on the orientation of the spin of the electrons involved. All right, so I said linear molecule in the ground state, excited state, S1 is transbent. And what we're showing here on the right-hand side are particular vibrational levels of the excited electronic states in the molecule. So if you look at S1, you excite with a laser, UV photon to that S1 state to a particular vibrational level and try and watch the decay. But this system is actually more complicated than I indicated on the very first chart, because near degenerate with the vibrational levels of that excited S1 state, we call it the bright state because it can fluoresce. We call this laser-induced fluorescence. That's how you detect the molecule as it decays from these excited states. The bright state, but there's also a host of dark states, near degenerate nearby. And in fact, there are actually 3 triplet excited states, labeled T3, T1, and T2. So there's an excited manifold of these T3 triplet states. There's a highly excited vibrational states of T1 and T2. And the real wave function of the molecule is actually all these states coupled together with some character. So the excited molecule takes on the character of these various vibrational states in these excited electronic states. The triplet states are called dark states because they don't fluoresce. So they don't reveal themselves through normal, conventional spectroscopic techniques. We have to detect them through some other means. And we talk about this term intersystem crossing, where the eigenstates are triplet, singlet mixed together. So how does one do an experiment where you probe the nature of an excited state of a molecule like acetylene and actually watch this decay, watch this mixing of these excited vibrational levels of these excited electronic states? That's the big question. So the work that we did in the field lab, looking at that picture on the left-hand side, this is your classic laser spectroscopy laboratory. You've got these pulsed lasers, there's a YAG laser, dye laser, frequency doubling techniques. All the work is done in a molecular beam technique, so you've got a vacuum chamber, pulse nozzle that's just like a fuel injector in your car. You form a supersonic molecular beam, travels downstream, probe it with a laser, and you're looking at the excited nature of the acetylene molecule. Now, as I indicated, those singlet states, they can fluoresce, and so you can detect that fluorescence using photomultiplier tubes and optics. The molecule that may have character that is triplet in nature, they don't fluoresce. They're the dark states. And as this supersonic beam travels down the vacuum chamber, those metastable triplet states can last a very long time, right? Fluorescence, molecular fluorescence in the gas phase, happens on the order of nanoseconds. These metastable triplet states are very long-lived. Unless they collide with another molecule, they really won't give up that energy. They can last for, in this particular case, hundreds of microseconds until they collide with the wall of your detector or do something else. And so really long-lived, they're high energy characters. So how did they decay? What's the mechanism? And one of the techniques we came up with is this technique. This acronym is a mouthful, obviously, but surface electron ejection by laser excited metastables, short CELEM. And the way this technique works is you have an excited molecule like acetylene, travels downstream, collides with a metal surface, in this case gold, and if that vertical excitation energy that the molecule is carrying is greater than the work function of the metal surface, in this case gold, 5 electron volts, an electron is ejected and we can detect that electron at a detector. So we've got these 2 different detection channels for detecting these excited states of acetylene. Fluorescence, biasing towards detecting the molecules that may be in states that have high singlet character, and CELEM, which detects these molecules that are excited in these metastable states. So perhaps we can start to watch the decay of the energy from these excited states. Now, let's get to some modeling. We developed 2 different models for decay. And at the top, we're looking at the wave function, really a mixture of these various singlet and triplet states in character. But there's 2 mechanisms. One is really just a pure statistical decay. You excite to an excited vibrational state in the excited state S1, the singlet state, the bright state. It decays to this dense manifold of these triplet states, which nominally do not fluoresce, but it just means that in the statistical approach, whatever vibrational level is near degenerate will just decay, and you can kind of watch that energy flow. But there's nothing really interesting about that. You know, just like we talked earlier about, Dr. Liddle talked about 1 degree of freedom, not very interesting. That's where the second mechanism comes in, which we call the doorway model. So perhaps there could be these very special doorway states of the third triplet state that are strongly coupled to the bright state. that can dictate and drive energy flow throughout the molecule. And this is the mechanism that we actually observed using the laser-induced fluorescence and sealant techniques. Now, why that's more interesting than the pure statistical decay is the fact that now perhaps you have a way to control the energy flow in the molecule. You may have some control over the dynamics. And from a chemist's standpoint, that's really interesting. We want to be able to control, manipulate the molecules, see how the energy flows, and maybe we can do something to affect the dynamics of the chemical reactions that a molecule like acetylene will undergo. All right, so I'll stop there, but the big take-home message about this first part of the talk deals with this is DoD-funded basic science, something that obviously I had personal experience with. But really, when we're talking about the balance between innovation, national security, and industry, the Department of Defense has been really good at, much like my colleagues from the other federal agencies, funding fundamental science, driving innovation. There's no immediate commercial application, obviously, with the kind of work that I used to do. But there could be, potentially, maybe 10, 15 years from now, something that comes out of the research that is being done at the academic level. Now, let me switch gears a little bit and talk about federal budgets. We've heard a bit about the DOE budget and NIST and some others, but I want to start with some data that I just pulled down from the American Institute of Physics. And so we're looking at the fiscal year 2024 science budgets for a number of federal agencies. Now, this data, take it with a bit of a grain of salt, right? Because in many cases, it's hard to define exactly what a science budget is. And when you look at these different federal agencies, obviously the work is very different in terms of the nature of the research and the science that we're doing, right? NIH, obviously, with roughly $50 billion focusing on health research. We talked about, Dr. Tannenbaum talked about the NNSA, the semi-autonomous agency of the Department of Energy, and we've got the other couple of DOE offices, the Office of Science and Applied Energy Office. If you look up at DOD, $146 billion in FY24. Now, we need to break that down a little bit to understand what does that money go towards. So DOD, this $146 billion is actually called Research, Development, Test, and Evaluation, RDT&E, right? So this chart on the right-hand side tells you exactly what it is. And there's two take-home messages out of this. So the first thing you notice is that there's the enacted budget, and as things go through Congress, we talked about some of the challenges with Congress and appropriations and the continuing resolution. But there's the president's budget request that the Department of Defense sends to the president, that goes to Congress, the House, the Senate. They can make changes as the budgets go up and down. The enacted budget at this point is really essentially the same level we had last year until appropriations come through. Perhaps that'll happen this month, perhaps not, we will see. But when you look at this chart, let's further break down the second point, exactly what is RDT and E. And I've circled in here a part of the budget that we call science and technology. When we looked at the DOE budget, we use kind of the very similar terminology, slightly different definitions, but S&T, what's written here is 6.1, 6.2, and 6.3, similar definitions, so basic research, applied research, advanced technology development. And then there's another part of the budget that is non-S&T accounts, so that's higher development. So things like prototyping, operational systems development, developmental systems. In the Defense Department, right, for the major systems that we look to build, whether it's the fancy new aircraft carrier or a fighter jet or a nuclear submarine, there's a lot of technology, a lot of components that goes into that work, and that's part of this higher development. Even before you build the very first unit of, say, an F-35 fighter jet, you've got to do the materials work, all of the sensors, the radars, the components. In order to get there, you have to do that higher development. Further, there's a breakdown between where this science and technology S&T funding lies, and it's between the military services, Air Force, Army, Navy, Space Force. And then there's a set of defense-wide accounts where I work, the Office of the Secretary of Defense. We hold some of that money. And there are other things. There's a defense health program that the Department of Defense runs, and another piece of this R&D work involves destruction of old munitions. All right, so one level deeper into DoD science and technology, and I'll focus in on the basic research. Now, as we already heard, this is where most of the funding goes for academic level research. All of the research grants that all of you and your principal investigators are working on in your laboratories, if it's DoD funded, likely comes from this pot of money here, roughly $3 billion for basic research. And if you look at the broader S&T funding, most of that is held, like I said, by the military departments. In the Office of the Secretary of Defense, OSD, a lot of the money is held with DARPA. And so that's where, for basic research, covering all that fundamental work. Now, at the bottom, this is interesting, the Undersecretary of Defense for Research and Engineering has put out a list of 14 critical technology areas that are important for the Department of Defense. Now, they're kind of divided into these three rough categories. There are some seed areas, fundamental research, that's things like biotech. We heard about quantum earlier today, quantum computing, but also quantum sensing and atomic clocks and timing. And Future G is essentially the next generation wireless technology. Then there are other more commercial adoption areas, right? We talked about microelectronics, for example. Advanced materials kind of straddles the fence between a seed area and some commercial technology areas. Renewable energy, space, microelectronics, as I mentioned, human-machine interfaces, those are all commercial adoption areas. And then finally, there are some defense-specific areas like directed energy, hypersonic systems, and integrated sensing and cyber, which is particular for the Defense Department. All right. So, in order to talk about how the department thinks in terms of finding that balance, innovation, national security, industry. Where I work in OSD is an organization called Cost Assessment and Program Evaluation. And we are kind of big strategic thinkers. We try and think about when the department decides to acquire a major system, a major defense program, how do we do it? How do we think about things? And we don't simply go out to Ball Aerospace or BAE or Lockheed Martin and say, hey, I need a new satellite, I need to put up a new satellite constellation, go out and build it. I don't say to Lockheed Martin, we need a new fighter jet, go build it. There's a lot of work that's involved in developing the requirements, the characteristics, the attributes of those systems. So this idea of the analysis of alternatives is something that provides the key information and the option space, the trade space for making these executive decisions. So we prioritize what the major gaps are, the capability gaps that the military needs for the future. What do we need? What does the technology look like? How do we accelerate and advance that technology to meet those capability gaps for the future? As the name of our organization says, cost assessment, those are the people who assess the cost of these major systems. And so all of the alternatives that we put forth have to deal with what's the cost, what's the schedule, what's the performance of that particular system. Now in CAPE, we don't actually do the AOA itself, but we help to guide the process of the AOA. So for example, if the Army wants to think about buying a new missile system, Navy wants to develop and field a new surface ship or a submarine, we help develop the study guidance that goes into the AOA for the organization that's doing the execution of the work. And once that study plan is complete, we approve the study plan, the owner of the program goes off and executes, and when the AOA is done, we assess that AOA for sufficiency according to the guidance. So this is a really important process in the Department of Defense for all the major defense acquisition programs. And the way we actually operate, we're several layers up. You know, you're used to dealing with the program managers of a particular scientific grant, whether it's a program manager at the Department of Energy or Department of Defense. We are not really looking at individual academic grant proposals when it comes to evaluating technology. We're really looking very broadly at big picture, strategic trades and options. So, not to get too mundane with this AOA methodology, but just to give a simple flow chart of how this process actually works. I talked about how CAPE, my organization, issues the guidance for an AOA, approves the study plan, and so on. So in the end, we desire a good comparison of operational effectiveness, the suitability for a particular mission, and the costs of each of these alternative solutions that we come up with. And there are a number of milestones to hit here. So in the first place, approving or denying a concept demonstration to proceed to mature technology to go into a system, that's the first milestone. Milestone B, looking at the engineering, the manufacturing development phase of this whole acquisition process for a major defense system. And then milestone C, once you decide to start production, at least low rate initial production of a new system, then you can start to do operational tests and see, well, what are the risks? What are the opportunities in deploying that system to the field? You want to get technology into the hands of the military, of the actual warfighter, but there's a lot of work that has to go on before you hand over a major system to the Army or the Air Force or Navy. All right, so let me get back a little bit to some fundamental physics. Now, this is at least a simple form of the radar range equation. And we'll break this down a little bit. You look on the left, you're talking about design parameters. So what do you need, what do you think about when you're designing a brand new radar system? Well, the design parameters, you want to know what the average radar power is, the area of your antenna, losses, the receiver, the noise temperature. These are all things that go into the design of a system depending on what application you're going for. On the right-hand side, we've got performance parameters. So here we have to understand, well, how will this particular instrument perform? So you've got the range, you want to know what the range is, how far it can see, the signal and noise, the radar cross-section of the targets you're looking at. And so when we do this kind of AOA work, there are a couple of things to think about, major trade-offs. The lower left-hand chart is a comparison of looking at cost and performance. Now, some things are obvious here, other things not so obvious. So obviously with cost and performance, you want to minimize cost, maximize performance, but you notice there's no real path to doing that. It's very rare that you have low cost, high performance, especially when it comes to a sufficiently complex system. So in looking at these different alternatives, we have to make some strategic choices. So for example, with alternative 2 and alternative 4 in the lower left of the plot with cost and performance, hey, yeah, there's a very low cost threshold to get those off the ground, but as you increase cost, there's only so much performance you can eke out of them, right? With alternative 3 and alternative 1, there's a trade. The lowest threshold in terms of cost, okay, you've got to meet that threshold, pay a little bit more money, and as you go up in performance, you can your costs go up. At some point, you're not going to be able to get more performance even if the cost of the system is driven up even more. So the choice between these alternatives is not always obvious. Sometimes you have to think about, can I quantify the risk of these alternatives? Not always. Sometimes you need a more qualitative approach to understanding this. On the right-hand side of the chart, we're looking at leakage versus coverage. So think about when you're designing a radar system to defend a particular area, right? You want to maximize coverage, cover the entire area you want to defend, whether it's, say, an Air Force base or an even larger area. Leakage refers to the number or the percentage of adversary threats, whether they're missiles or aircraft that could leak through your defenses undetected. And so obviously you want to minimize leakage, maximize coverage. You can't always do that in every case, right? So there are some choices to be made here. How do you make those trades? Do you want to have a small number of very expensive, highly capable radar systems, or can you get away with a more disaggregated, dispersed, larger number of less capable, but to fill in some of the gaps, fill in some of your coverage gaps? So those are big trades to be made here. All right, so I'd like to end with a connection to 2023 Nobel Prizes. And I don't need to go over this work, you're obviously familiar with that. In fact, you've heard from a couple of the Nobel laureates this week at the APS meeting. But I want to make some connections to some funding that the Defense Department has done with this pioneering work in the past. So in both the physics and chemistry Nobel Prizes for 2023, I'll highlight first with the physics prize for attosecond pulses, Ferenc Krauss. The Army Research Lab, the DevCom is the development command for Army Research, we funded with a short-term innovative research grant the work, and again, it's a modest amount of funding to get work off the ground, but the work that was done at Max Planck Institute really starting to, at a fundamental level, contribute to the development of this Nobel Prize winning work. And keep in mind, this kind of work, obviously there's many different funding sources. There's small components that feed into many years of work, but the Department of Defense has been really good at creating new fields of science, driving innovation from the very beginning, where the NSF in partnership with DOE, these are fundamental government-funded programs out in the academic world that have really proved to be very innovative in driving a lot of the great work that's going on across the physics community. Likewise, the prize for chemistry last year, Professor Buendy, MIT, has been affiliated for a very long time with an institute that the Department of Defense has funded for decades, the Institute for Soldier Nanotechnologies. So this is an interdisciplinary center that the Army established a long time ago. And so here's a connection between innovation in the academic world. There's partnerships with industry, because this is really a center that drives those partnerships out in the industrial world for commercializing techniques, and with the federal government. So while ultimately we fund scientific research that deals with potential uses for the future in sensors and secure communications and enhanced imaging, driving the national security enterprise, really we understand that funding fundamental basic research is critically important for future advanced capabilities. And so managing this entire ecosystem is a very complex enterprise. It's a difficult endeavor, but I'm glad we have this partnership with the broader physics community. All right, I think, looks like I am done.
Thank you, and we will now take questions for our speaker, and remember to come to the microphone so the recording can capture you.
Thank you, a very interesting talk. So you mentioned $146 billion. Some of that goes towards test and evaluation of new projects. Seems to me that didn't work with the F-35 because they keep failing. Okay. And the other point I wanted to make was, so we have this appropriations process that's going on. So you're making, your department helps senior managers to make decisions, but then we have a lot of lobbyists who are sitting in Washington, D.C. They're also influencing the appropriations process. So does that disappoint you when you've gone through all this big trouble to make these, help people make decisions, and then you see some lobbyists come in from Lockheed Martin and suggest that more money be spent? Anyway, that's mostly comments for you. Thank you.
Thank you very much. Yeah, so there are, of course, challenges with Congress and appropriations, as you as you mentioned. Now, all we can really do is defend the defense budget on the Hill. Working with Congress is a critical part of what the Defense Department does. You know, we, as civilians in the Defense Department and the military also, we are, of course, apolitical. We stay out of the politics. We are directly affected by the politics and what happens politically. Of course, that is a challenge. I'd say for the challenges of having the continuous resolution, it does pose challenges in getting things done. But that is the risk. We understand how things are happening on the Hill. It's interesting in how things play out in being able to start new programs, given the budgets not having the appropriations in place when the department wants to execute. But that's part of the job. I mean, that's really managing that risk, managing those challenges are things we definitely have to work through.
Hello, thanks for the talk. And I work for the American Institute of Physics, and a person on my team made those the tables of funding numbers for DoD. And so
oh, great.
Really
well,
appreciate you using us.
Thank you for the tables.
That
yes.
data. And we have just this Sunday they finalized the appropriations for a bunch of other agencies. DoD is still pending, but if you want to know the budget for DOE, NIST, and so on, we're updating that very actively. But my question is, can you go a little bit more into, at the end you were talking about the rationale behind why DoD funds very fundamental research in universities and views that as important, even though it's traditionally the general perception of the Pentagon is, oh, it's all going to be secretive work. But can you talk a bit more about the rationale for funding this very open work, but also if that's changed at all? If you sensed there's a lot going on in research security policy, and I think DoD is very actively rethinking its approach to funding fundamental research. And can you speak at all to that?
Absolutely. No, that is a very good question. Now, obviously, with protection of national security, there are classified programs, a lot of classified work going on in the department. But I'd say for the basic research enterprise, the folks who, both in the services and in the Undersecretary for Research and Engineering, it's critically important that the basic research be open, collaborative, and shareable. Right? We take enormous advantage in being able to collaborate globally at a conference like this. So there's real value in doing that. And the thing about the basic research that's really important is that, as you kind of alluded to, the main product is the generation of knowledge, and we understand that, right? So you're not looking at an application where you're going to create a widget or a product that's going to go into a system. But having that knowledge is really important to drive future capabilities. And so maintaining that open, collaborative scientific enterprise is really important.
All right, and with that, I will bring this session to a close. Let's thank our speakers again for
Exceeding my expectations. I really enjoyed this. Thank you.